Yeah.
That wireless suggestion you made to me yesterday did not work for me. It actually made it actually made things worse for me on the
Really?
WN.
That's interesting. What? You IWN, right?
Yeah. As in
the 7260 or something like that.
Yeah.
I'll go on the inside that way. I'll give you a second. Can you email me your the WN0 info from Garcia.com? I don't need the whole thing, just the.
I'm actually using a script to so I'll send you the script.
I had the same exact problem, and I don't think background scan is the problem, but disabling that air quote fixed it for me. So something clean.
Thanks for the suggestion.
Yeah, I wish it helped. That would have been better. I don't know if I don't know what I'm more offended by, Mr. Barber or good morning.
That is very warm. That will be constituted warm.
Started, everyone ready?
Morning, Dan.
Morning, Dan. Welcome to BSDCan 2016. Show of hands, who's here for the very first time? Okay, leave your hands up. Wow. Leave your hands up if you're here for the first time. Okay, everyone who's been here before, look to the nearest person who has their hand up. It is your job later on this morning to introduce that person to two other people here, okay? Two other people here that have been here before. Ask that person who had their hand up what they're interested in, and then you find someone else here at BSDCan who is also interested in that, okay? Anyone not want to do that? And usually the person you want to introduce them to is Peter Wenner.
Actually, Glenn.
Could I speak up? Can we turn the volume up a bit? Andrew? Yeah, we got an echo. There's an echo.
There's an echo.
So if I just talk loudly, you can hear me okay? Or is it just that the speaker is doing it weird?
More people are just saying.
Groff is in the house.
Out of my hands.
No. This is responsible for him until the end closing session when he gets.
You don't know what you're asking for. You'll end up at the oak anyway.
No. Andrew is responsible until the handover, which is at the closing session. Is that better? Hands up if there's an empty seat. People are looking for seats.
2 seats.
2 seats. 2 seats down here, seat.
That's not the auction yet.
For the new people, there are a lot of interesting things that happen during the open session. Maybe that's the closing session. All right, well, no. Every afternoon is a closing, changing the guard section on the Parliament Hill. If you've never seen one, don't see one. Don't do it today, tomorrow. One of the things we wonder, there's only a few people that have been to every BSDCan. Who's been to every BSDCan? David Maxwell? Kurt? Okay, so that's 4 of us. All right. How many missed just one? How many missed just 2? And the guys, one of the guys that's missed just one is Andrew. Put your hand up, Andrew. He's the AD guy. He's been with us every single year from U of O. So, in this session, we're going to go through the sponsors. We have a few points of order that you should know about the conference. We have some prizes, some hardware to give away. And then we're going to go on to the talks. And I also have a short little discussion about a clock. You'll be interested in that, maybe. Okay. IA Systems and EMC have been sponsors for a very long time. Thank you. Not just for these sponsors, but for all sponsors. If you have day-to-day contact with those sponsors, tell them, hey, I noticed you sponsored BSDCan, and tell them why BSDCan is important to you.
I'll pass that on then.
FreeBSD Foundation, Google, and my employer, Talos. Carson, who doesn't know Colin? 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 Rod Drawings. Colin. If you don't know who Rod Drawings is, look it up. You all know who Intel is, and you FreeBSD Conference guy from FreeBSD Con, yeah. NYI hosts a lot of infrastructure, including some of my servers. Backers is here, and Microsoft. If you don't have your coupon for a VM, I'm sure you can still get one. Thank you. Anyone not know Alan? Alan's down here. Am I pronouncing that common right?
That's
Okay. Say it
comune, I guess.
Okay. Thank you. Thank you.
He's here. That's Commune is here as well.
Where?
Where is he?
Oh, over here. Domo, Lennox, Michael, where's Michael? Mike's here. Thank you, Michael. And Shopify. And with BSD inside, we've got NetApp and PlayStation. Yay, Now, the program committee does the job of reviewing the submitted talks and deciding which ones you don't want to hear. And that's harder than it sounds, because sometimes you get down to the top N talks and it has to be N-3, and we can't figure out which 3 talks are the least deserving, because that part is actually very difficult. So if you see these people, ask them, can I be on a program committee? So think about that for next year. Thank you. Is Jennifer here?
No.
If you were at registration last night, you might have met Jennifer, she was there for a little while. All the speakers have heard from Jennifer, but probably not met her, but she's been helping me out now. This is the second year, third year, I think, of doing a lot of the things that allow me to do the things that only I can do at the moment. Drew's on the registration desk. Drew's been here every year. I'm sure she's been here every year, even from the days when she used to live in Ottawa. Adam Thompson does a lot of work for me, talking to the hotels and getting the website up to date. And Brody, is Brody in? No, Brody's been doing a lot of running around for me. Please go get some photocopies. Please go get the badges, stuff like that. Thank you. Okay, lunch is in about 3 hours. So if you're going to the BOF, our BOF is a birds of a feather session. Basically, you've got a topic and you'd like to talk about it, and a bunch of people all get together and talk about it. It's different from a lecture where someone stands at the front and goes on. Instead, you're all talking amongst yourselves about an interested, a common interest. So grab lunch, go to the BOF runs the schedule. It's going to be snacks and coffee 2:30. Later on tonight, 6 p.m., there's Jock Sprints in DNS 1120, which is just over here. Hacker Lounge is in the ground floor of residence. That's on the map. Everyone is welcome here. You don't have to be a coder. You don't have to be a computer or anything like that. Just come in, bring your laptop, there's Wi-Fi, hang out. Tomorrow morning, don't show up so early. There will be food and beverages out there, just like there was this morning, only it's an hour later. Oh yeah, when you're in the Hacker Lounge, bring your own extension cord, it always helps. Leave it tidy, ground floor residence, every night, Wednesday to Saturday, but you can't be there Friday morning from 6 to 8 a.m. There's another
3 hours ago.
Yes. Last person to leave, lock it up. If it is locked, the key is at the ground floor registration desk, lobby, hotel check-in thing. This list of BOFs may be out of date, but I talked about the BOFs earlier. There's one on ZFS, there's one on Haskell, there's a meta BOF, which is all about user groups. Isn't that George? Is that right, George? Bacula and backups, I'll be doing one on Bacula and backups. And then there's one on BSDs and privacy technologies.
There's also SDR.
SDR got added later, I'm sorry. I created these slides before that.
It's not SDR.
Sorry?
What people with SDR sounds cool.
What does SDR stand for?
Oh, software defined radio.
Software defined radio. So basically you get a radio, you plug it in, it works. Like USB. We give you these lovely bags with Intel on the outside. If for some reason you can't find enough room in your luggage, give them back to us. we give them to a food bank. They use it to have their clients take food home with. The very bottom of every event in the schedule is this little feedback thing. It's out of date, I think. This is 2 years ago, but it's click on that, give your feedback, let me know how much you like my session. Okay. Somebody? Ooh, look around. Have you lost your ticket for the party? Because someone just found the ticket for the party. Now I have 3. No option at all. All right. We have a hardware giveaway. Sean Webb from FreeBSD has some hardware that he wants to give away. And the way we're going to do this, who's the oldest here? Put up your hand. Who's over 70? Who's over 60? How old are you, Jim?
62.
What am I? You older than 62? I guess you win.
So this is a Raspberry Pi 3. It includes already the SD card that I need with it and a serial cable, so it's completely ready to go. Main purpose for this is to get BSDs running on the Pi 3, so we can take away some market share from Linux.
So the easiest way to do this, if you can get down, you get it now, please. Otherwise, someone will try to impersonate you later. Now, the next one is the youngest one. I think I already know who that one will be. Is there anyone here under 20? Who's under 20? Anyone else? Anyone under 18? Yeah. Anyone under 18? Okay.
You're in 20 in like some weird date.
There's lots of ways to figure out how to use this. Who got their source commit bit in the past month? Anyone in the past month get their source commit bit in the past month? Sit down, sir. Sit down.
What's the show, how long ago?
You tell me.
Well, that was more than 1 month. Oh, yeah.
Anyone less than a month? Anyone 2 months ago? Anyone?
All right. Hard BSD, sorry. There's too many repos.
I'll hand it to you since I sit next to you.
I think I'm going to win the next one too.
Let's give it to Rod.
Yeah. Rod or Kurt Club?
Who's going to till later?
No.
Rod has the oldest UID.
79.
FreeBSD project, yeah. This is across all.
Is that a BSD project? I think it is.
It was surreal voting on Kurt's commitment. So Rod's older for FreeBSD.
Do you want to make it for FreeBSD or for BSD? Because
The candidates are arguing about who's older.
It's any BSD.
It says any BSD.
It clearly says any BSD.
Sean.
Would you work with it though? Would you use it?
The error would.
Okay.
I have one already, so,
You sure?
yep.
All right. Solve that. Well, thank you. Thank you very much, Dan.
Thank you, Sean. One of the benefits of running your own conference is you get to stand up at the front and talk about something that nobody wants to listen to. I'm going to talk about a clock. And the reason I'm going to talk about a clock is that listening My girlfriend Kathy is an NP practitioner with a specialty in geriatrics. When you get older, one of the things that they do is to test how your memory works. And one of the things they do is they get you to draw a clock. And then they get you to draw a time on that clock. And I listened to a radio broadcast about a guy who had great difficulty with this. He completely forgot how to draw a clock. And so what he did is he sat down and analyzed what a clock was. And he found 3 different levels to a clock. And when you listen to these 3 different levels, you find out what a terrible design a clock is. It is not logical at all. For instance, the biggest hand denotes the smallest unit of time. And the smallest hand denotes the largest unit of time. And the middle one denotes the middle time. So, and what's even stupider is that the same values, the same numbers represent different values depending on which scale you're reading it on. So, this may be noon, but it's 1 minute after noon, but it could also be, you know, even explaining it is hard. Like, this is 5 minutes, or it's an hour, depending on which scale you're using. If a clock was to be designed today and submitted as part of the UI, people would ridicule it and say, that's terrible, it's absolutely stupid, why are you doing that? Nobody can use that. Yet everyone here, I assume, knows how to use this. And everyone considers it. You look up the clock and you can tell what time it is right away, just like that. There's no thought process really involved that you can see it. So it's actually not a bad design. But if you were to see it for the first time and you listen to the points I just made, you say that's terrible. It would be flamed to crap on any user list, I'm sure. Anyway, thank you for.
Dan.
Yeah.
It's also not specific.
Yeah, saying or repeating me? What?
That time applies to 2 different points in time each day.
It was pointed out that the given clock face represents 2 different times a day at any point in time. Yeah. So just because it seems stupid to you when you first see it, give it a little bit of time. It may actually turn out to be the best thing ever. So following on from that, everyone was here for the first time at some time. So don't be so judgmental of people that are here for the first time. Welcome them in. Tell them what beaver tails are. Tell them why they should come to the closing session. Sorry? And don't push them into the sinkhole. Any questions so far? If you're type 1 diabetic, beaver tails are not the best for you. Anyone else? Any other questions? Because if there's no more questions, you go on to the talks. Do you really want to go on to the talks?
No.
We want to hear you.
I thought so.
More clock.
Question.
Yes.
What is this year's charity auction recipient?
Good question. This year's charity auction recipient, as in most previous years, is the Auto Mission. If you ever walk down this street into the market, the Auto Mission will be on the right-hand side. And they get the results of this conference and the other conference I run, which is BGCon. And I forget the amount they got last time. I think it was, do you remember that? I can't recall. It's on Twitter somewhere.
It was like $1,500 or something like that?
$1,500 or something. And it all gets raised from the charity auction at the end, where, yes, I auction off a cookie. And I auctioned off at the Postgres Database Users Conference, I auctioned off a toothbrush.
Clock, many of them cross square, and then a box and a box and a box and a box and 2 dots and a box and a box and a box.
You know, but that's what we'll do when we're old.
We'll draw a phone, come on.
What do you mean when?
just think of these things.
He said he just thinks of these things. I'm sorry, Lindsay. Okay, so I guess it's on to the talks then. Have a good time, and if you have any questions, ask the registration desk, put it on Twitter or Facebook or something like that. Hashtag BSDCan. Thank you. See you soon.
Thank you, Dan.
Whoosh.
Hey, Warner, I wanted to ask you, do you have anything in your applications folder that's not on your dock?
Yeah. Do I have anything on my app? I don't know, you guys are running.
We're gonna learn about things faster than he would.
We got play mode running, I'm gonna be talking faster than Robert Watson.
It's not possible.
To keep up, I'd have to. I think you're right. I think I would follow my mind. My voice amplified? Excellent. Okay. So the URL that's on this is actually a copy of my slides. Like I said, I have a checkered past with laptops at conferences. So far this year, no shoe incidents. You had to be in Paul Henning's talk. I was trying to fix a disk drive with a shoe one year. It didn't work out too well for me, whether it's
What about the shoe?
Didn't work out okay for that.
Paul was able to ridicule me in public, so I think, yeah.
And where did the shoe go? It was auctioned off.
The shoe wound up in some big noble landfill somewhere, I'm sure. I did not think to preserve it for posterity. That would make an interesting exhibit one year, though. Have just get a table like the foundation does, except, you know, this is the laptop I melted. This is the laptop that I broke during Paul Henning's talk. This is the shoe I used to fix the disk drive.
Give the shoe to Dan to auction off.
Oh! That's brilliant.
Slightly more sanitary than a toothbrush.
Combine the two.
Well, and think of all the value behind it as far as nostalgia is concerned.
Yes, unfortunately, all of these artifacts have parted ways with me. It would be difficult to track them down.
They haven't ended up in your garage like some of the computers you used to have?
All those are in my basement now.
Ooh.
And I have a very small fixed space for that. And so I've been purging to get from, you know, a room this size down to a room the size of this lectern in terms of old computer stuff. So I don't have any 486s anymore.
So no one's able to test out, what was it, the ISA card that you had? Oh yeah, that's right, I think you said that.
I had a big pile of ISA cards that left at the same time, too.
Yep.
Those left prior. I tried to give them to Matt Dodd, but he said that he already had too much useless junk in his house. And if more arrived via FedEx, his wife might kill him, so.
Matt Dodd told me no.
Yeah, well, they were next to the Spark Station 5s that you gave me a long time ago.
I've got some PAS hardware that could take these.
I have a machine that can take these cards. That's, Wilco sent me a Jack was throwing it out, and he managed to snag it for me because I foolishly mentioned something about ESA. And next thing I knew, I had the machine, and then memory showed up at another CPU. I kept it for years, and it was, I finally just had to let that go. You know, one of the too many projects in my life. Right, I need to turn off the internet.
Just in general.
Why weren't?
Getting a hold of Brian, just wondering if the IFC connections are too high.
Let's just say some people
Increase.
like calcite too much.
Some of us like it just right. You have to turn off the whole
Because you're
introduction.
too down to IP,
Yeah.
so.
If it gets rid of the
I-
calcite, it's a small
you
part.
have-
That makes
you have
sense,
to
actually.
keep
That's
that
like
down. No,
That sounds great. I didn't tell you that.
they didn't tell me that.
I only ever true.
Yeah. You take Swedish kroner.
Not anymore.
Well, it'll take me a while to arrange that.
Not until the next bureau is
It's back in Sweden.
this is Croatia this year.
They don't really mind the well,
Is this the technical one?
Yes.
Okay, good. It's the right place.
I hate to break it to you. That's only but one corner that will be heckling me today.
That's the amateur corner.
Yeah.
Okay. I don't know, we all have to start somewhere.
I don't know what makes you think.
Past experience.
There's no indication of future returns. In some cases.
I eventually got it.
Past is prologue.
So probably I got logged on.
No, this
The
one's mine.
NVMe Express community doesn't have a representative from any of the BSDs. They have representation from Linux and from Windows, but no BSD representation.
How would I correct
All
that?
the analysis and the right
Your employer needs to join, it's like advertising it and shit, and then you can get applied to the BSD tools.
I may have to do that, although Intel wrote the FreeBSD driver.
Right.
And so Jim Harris may be on those.
Jim Harris is on, yeah.
So, look into that. It's a good point.
Just stop recording you now, just so we've got. Just don't forget. But this bit will get edited now, so
Yeah, I won't say anything too bad, but I also don't have the mic on.
Okay, don't show anything on the screen. You don't write some nasty notes to guide to the post headers. Again, probably kind of.
What?
You're in the right place? I can only move this so far. It's on a leash.
There's Yep.
So we'll get started here
I
in
know.
1 or 2 minutes. Right at 10, give everybody a chance to arrive and settle.
Yeah, no, it's actually down to Tuscany, I think. Maybe. Maybe I shouldn't have added them. I think they're pretty outdated, so, yeah, I actually don't want these. I don't know. Facebook. That's the one. Google Plus. Okay. I'm not literally is just NGI. Yeah. So lately I've been working on priority fixes on BSDC. But originally when I came on, I started working on build system enhancements to
Okay, it looks like everybody's here that's going to be here. So I'll go ahead and get started. My name is Losh. I work for Netflix, and I spent the last several months exploring the mysteries of CAM. When I submitted the talk, I had this rather boring title, NVA, the NVMe CAM attachment. And if you want to grab the slides, they're available right now. For some reason you want to follow along at home. But the real title of this talk is How I Learned to Stop Worrying and Love CAM. Because it kind of reminded me of a bit of a wild ride that the folks in the bomber took when everybody went crazy in that Dr. Strangelove movie. So. Like I said, I work for Netflix. Most people here probably have heard of Netflix. Has anybody ever watched Netflix online in here? Okay, everybody. Yeah, how many on the FreeBSD laptop? Can you raise your hand, Mark?
Laptop. Can you watch Netflix on it right now? Not yet. Working on that.
We know who to call to get the right string in so that the browser works. Yeah.
Doggone Silverlight.
I'm sorry, what?
Oh, doggone Silverlight.
Yeah. Anyway, Netflix runs its own CDN. I believe a few other people in the room that don't work for Netflix also run CDNs. Is that right? Everybody from... Okay. Anyway, one of the things that we do at Netflix is operate at a fairly large scale as well. We have, is it 75 million yet, Scott? The number of subscribers worldwide? Something like that. We don't have 100,000 yet. There would be a party for that. 100 million, sorry, 75 million. We need to anticipate the future. So when we're streaming in the evenings, according to Sandvine, about 1/3 of the internet traffic, I think 39% in their last report, is Netflix-related videos. So we're streaming terabits a second from all of our machines, all our thousands of machines around the world. This is a picture of some of our storage boxes that we have just racks and racks and racks of. So when we started the CDN, we had a bunch of storage boxes with hard disks with some flash to boot off of. Then we thought, well, flash is fast. We need to build some offload devices, some flash storage devices. Anyway, we built some flash storage devices based on SSDs. And those worked out for a while, and then we got faster machines and needed a faster interconnect. So along with the rest of the industry, we're transitioning away from SSD drives to NVMe. And these happen to be Intel drives. We may or may not be using Intel drives in our product, but it was the picture that I had. They come in two form factors, either the hard disk lookalike form factor, which has the PCI lanes in a special cable to it, or an actual PCI board.
It's when you look away, I'll pick up when you look away.
Okay. Maybe I'll just do this. So what's motivating the move to NVMe? A lot of people probably have heard about this, yet the reasons for going with NVMe have not been well explained, perhaps. So when you have spinning disks connected via SAS or SATA, you have very high latency, so it doesn't matter how much protocol overhead you have. The long bars, clearly shows that you have like 20 milliseconds of latency and then microseconds of protocol and software overhead. But as devices got faster and faster, and you wanted to increase IOPS and increase bandwidth, the software time and the protocol time started to matter a lot. So Intel went out and designed NVMe Express to try to overcome some of these limitations. And this graph shows the second generation card that has like a 60 microsecond latency. Some of the latest Gen 3 cards actually get down to 10 or 15 microseconds of latency. So any software overhead, which used to be just in the noise, is now can be a significant part of the latency. FreeBSD can get full bandwidth from the NVMe cards that we've been using, thanks primarily to Drew's efforts at optimizing our whole network stack. We get good latency with FreeBSD, but we still need some optimization. We're about 30 microseconds. We could optimize out maybe another 5 or 10 if we look at the stack that we have on FreeBSD a little more closely. So one of the big questions I always get asked when I tell people I've done this, hey, I wrote an NDA, or I wrote a CAN front end for NVMe. People are like, why? There already is a disk front end for NVMe that Jim Harris wrote, and it seems to work fairly well. Well, this is true, but when we were evaluating NVMe, it became obvious to me fairly quickly that it would be very difficult to take advantage of the IO scheduler that I've written for CAN to adapt it for the NVD driver. One thing to know about Netflix is we like to buy the lowest cost drives that are performance. And sometimes that low cost, you get kind of what you pay for. We can put more drives in the system, that gives more redundancy. So We buy drives that happen to fail a little bit. If 1 or 2 drives fail, we still have enough drives in the system to drive traffic and to have it be a useful system. But usually what happens is we'll get the drives in, everything looks good, we'll deploy it, and then we'll find some scenario in our workload where the drives are quirky. Oh, it can write at full speed only for a while, and once you write 10 or 20 gigabytes, the drives no longer behave at full speed. If you give it too many writes at the same time, it can have problems due to the problem with the firmware of the drive. So the I/O scheduler that I wrote and talked about last year smooths out all the performance goals, and we figured we would need to do this if we were deploying NVMe. So this talk will be a little bit about how I did it, but primarily it will be about CAM, all the pieces of CAM, how CAM fits into the system, a little bit of the bigger part of the I/O stack, so you could understand what CAM's role is in that, as well as understand the code while we're, if you were to go look at it. So we'll start with the FreeBSD I/O stack. This is a picture that I took and adapted from Kurt's and George's book on the design and implementation of FreeBSD. I simplified it a little bit and added the upper and lower designations and added the different pieces of CAM as well as a couple of the other drivers that are in the system that don't use CAM but do similar things. So this should be familiar to most people. The upper part of the stack, which is the top part of the picture, primarily focuses on the VM system. It's the buffer cache of the system. This is what allows you to touch pages and eventually they wind up on disk. But the actions in the upper part of the system are loosely coupled to the lower part of the file system stack. That means that if I make a page dirty at the upper layers, maybe it'll get flushed to disk now, maybe it'll be flushed to disk later, maybe I can change it a few more times, but there's not a direct, I touch the page and it goes to disk. At the next layer down is Geom, which handles partitioning and stuff. You could go look at one of Paul Henning's talks about that if you want to learn all the details of Geom. I'm just going to touch on it lightly here because CAM fits in underneath Geom. And CAM handles queuing and scheduling of I/O, handles freezing the queues when there are errors so that error recovery can happen if an I/O resume. It enforces different rules about what you can send to the drives, what the hardware system can support at any given time as well. If there are limitations, if you have a lot of disks on a particularly an older disk controller, SCSI controller, the disks might be able to do a bunch of I/O, but the controller can only have so many outstanding I/Os at once. So CAM handles all of that behind the scenes transparently to the user. Last year I talked about the CAM I/O scheduler. I wanted to include pointers to that this year in my talk so that people can go find it, maybe watch the YouTube of it as well. If they wanted to read about the I/O scheduler in more detail so that they can understand, so you guys can understand why we wanted to use it. Basically, it collects real-time statistics that we find useful and helpful in managing our systems, as well as shaping traffic to the drives, to keep the drives from saturating and going into overloaded, into a mode where they're overloaded and don't perform well. Okay, so when I was preparing this talk, I realized that there are a lot of things that are going on in the system with CAM that depend on the upper layers, but aren't actually part of CAM. So I thought I'd touch on that just briefly. the design implementation book covers the buffer cache and the upper layers fairly well. So I thought I'd just start there. You know, a file system or maybe a swapper or pager that's paging things in and out, reading and writing things to the disk. And it calls a bunch of stuff that eventually winds up as a B read or a B write, which calls the strategy routine for the Losh. And that winds up calling into geom. So the red part here, the blue part is the buffer cache. And then the red part is geom, where it converts the struct buffs to bios, and then sends it down through all the layers, and eventually winds up at the geom disk layer at the bottom, with a bio that's going to go to the disk exactly ready for the driver to deal with it. Drivers don't have to deal with partitioning, they don't have to deal with striping or anything. By the time the driver gets the command, it's ready to go. It's get this block, get this length, and go. And that's the layer that I'll be talking about for the rest of the talk, the CAM layer. Another way to look at CAM is that we have the requests coming in the top, and they're dealt with by the perif drivers. A perif driver, I'll talk about this in more detail, all of these things in more detail, but briefly. A perif driver is a driver that takes I/O requests and turns them into some kind of protocol. It will take a block read and turn it into a SCSI read 10 command, or an ATA command, or a tape command. Or it will take an ioctl with a protocol block already formed and just pass it through. It passes it off to the transport layer. One of the things that took me a while to understand with CAM a long time ago when it was first committed was I saw all these XPT things. And it's like, XPT, what the heck is that? And that's just transport. And the transport is responsible for taking these protocol blocks and giving them to somebody that can actually talk to the hardware. And that something is called SIM. It's a system interface module. The name is the same for ATA or SCSI or whatever. I listed a few of the SIMs. I thought about listing them all, but we have like 30 or so in the tree right now, and that would make this slide ugly. But the SIM takes the requests from the transport layer, sets up DMA to send the request blocks to read data, write data, whatever, gives it to the hardware. And as you see at the bottom of the screen, and then the hardware does its thing, the drive does its thing, and eventually an interrupt happens, and then the process reverses. The SIM notifies the perif that the IO is done, the perif calls bio done, it goes up the stack, calls buff done, or one of the variations of it, and the IO completes. So I was talking about the different layers of CAM. I was talking about the perif, talking to the XPT, talking to the SIM. And all that's done through a generalized message passing system called CCBs, command and control blocks. These are the messages that flow back and forth between the various parts of CAM. They're present as one giant union of all possible messages, so that the action routines that I'll talk about later, they have a nice simple prototype and don't have to cast await pointers. It helps with type safety a little. When you create a CCB and hand it off to be executed, some of the commands will execute right away. You can ask the transport layer about details about the transport. And the transport layer goes, oh, I know those, fills in a little structure, and completes the CCB. Others, obviously, are queued. I want to read a block off of the disk. Well, you hand that off, it goes down to the SIM. SIM can't complete it right away, but it starts it, marks it as started, and returns. And then when the controller finishes the I/O, it will complete the CCB. We know about the users of the CCBs know that the CCB is completed because there's a callback routine that gets called. In some cases, you set up the CCB, you call done on the CCB, and that done routine actually does the thing that that's requested. It's almost like you're just completing it, and as a side effect, you get the information you want. That's one of the things we go off and read the CAM code that can be a little confusing. It's like, this bit of code set up the CCB and then called done. Well, how does that work? Well, if you see the callback routine that it does, and go look at that, all the work gets done in the done routine. And once a CCB is completed, we have a number of status. That's basically two parts. One part tells whether it's successful or not, and the other part tells details of how it was successful or unsuccessful. So I also talked about the different layers, messages that pass between them, but I didn't talk about how, what glues them together. CAM paths are what glue them together. They describe different nodes in the tree. And all the physical objects in the tree may have one or more paths. For example, in the system I'm running, I have the pass-through driver and the DA driver to talk to my two SSDs. And as you see, both of them at the bottom here in the CAM control data list, as you see, both of them have both DA object or DA driver attached to them and a pass-through driver attached to them. And you can talk to the physical devices in a number of different ways. And CAM's paths help deal with that. We ref count the topology, so as more instances, more drivers attached to a particular instance, we're able to keep the resources around if other drivers go away. It used to be the case before all the bugs in the SCSI or the USB removal code got fixed.
Hooray!
Yay! That you pull a USB drive out, and USB would do its thing perfectly, or not, usually perfectly after Hines has worked on it, and but you get a rough count error, so you would not be able to detach it, and you'd have to reboot. And that's what this is a result of, the rough counts on the topology. There were bugs so that when things went away, rough counts weren't being decremented, so you couldn't unload drivers. Another piece for CAM that you need to know about is the async notifications. And the async notifications are just a way to broadcast information or broadcast that something has happened to different parts of CAM. And this is a very integral part of many things in CAM. It's used to enumerate the drives. It's used to attach device drivers to those drives. And it's used by the SIM to tell attached drivers that something interesting is happening. Some devices need special handling after a SCSI bus reset, for example. And when the SIM detects a SCSI bus reset happening, it's supposed to send a bus reset asynchronous message. One of the things that's interesting about CAM is, relative to NuBus, is the model of finding devices is a bit inverted. The SIM, which you'd think would know about the devices, doesn't tell the rest of the system the devices are there. The rest of the system tells the SIM, hey, go scan for devices. And the transport layer finds the devices, gets all the information for them, and then sends, hey, I found a device, to all the drivers that are listening, and they go do their thing. So I'll get into that in a little bit more detail. In NuBus, in contrast, NuBus would say, I'm in an attached routine, I know what's going on, I know what my children are, let me tell NuBus about the children, and then the children go off and probe and attach. So it's a little different mindset. Both of these systems were created contemporaneously, and so each chose a slightly different way to model the devices. Earlier, when I was talking about what CAM did for the system, one of the things I said was that it handled queuing. Modern disk drives have a number of slots that you can put IOs into. With SATA, they're tagged queuing. You have 32 slots. You put the IO in. CAM's dev queue mechanism ensures that you never send more than 32 IOs down to the SIM for a drive. So you can't overflow it. The SIM has to deal with it if you accidentally do, or for some reason through error handling, it winds up with more than it can handle. But for the most part, we try to pace it so that we always have just the right number of requests in the drive. And this can be dynamically resizable. At Netflix, even though our spinning disks have 32 slots, we find we get better performance if we only use the first 16. So at runtime, we set it to 16. Other people use this to say, well, I've monitored the drive somehow. I know I can handle 8 right now. And then later, I monitored the drive some more, and I can handle 12. And dynamically grow and shrink the number of commands that they allow. In addition, the dev queue can be frozen for error recovery. One of the interesting parts, unfortunately, that I won't get into too deeply today is in CAM, the dev queue freezes and thaws for various parts of the system. So when you want to submit IOs, but you know the underlying layers aren't ready, you can freeze the queue, submit IOs, and then when you know the device is ready, you unfreeze it. This can happen during startup, but it can also happen during error recovery. The typical error recovery for most disk drives is cancel all the IOs that are present, do something special for that one IO that failed, and then resubmit the IOs. Well, the dev queue mechanism lets you freeze the dev queue, so you have all the devices there. No new commands will happen, and then you can go deal with the error recovery, and once that's done, you can unfreeze it, and all the normal mechanisms for queuing and stuff apply, and you go from there. Yes?
Are there error types that might cause problems with the queuing that you have to worry about, or is it okay to just keep that paused?
When you have the queue paused, it's only a problem if IO needs to complete. So if you have a drive that's failing, let me repeat the question. The question was, are there error types where you have to worry about the queue filling up? And there are some errors, like if the hard drive is spinning or has a bad, has a bad sector on it. And you have to keep retrying that one sector, or maybe it's a group of sectors. The dev queue will likely fill up with other requests that people want to do while you're doing that error recovery. Eventually, you need to terminate the error recovery or the system becomes unresponsive because, like most preemptive kernels, FreeBSD really wants to be able to do I/O, to do anything interesting. So now that I've talked about the various bits that glue the periph, the XPT, and the SIM together, let me delve a little bit more deeply into those devices. CAM peripherals, like I said, implement some protocol. They take block I/O requests. And convert them to SCSI read requests or SATA read requests or something. But in addition to that, they participate in device enumeration. And I'll get into exactly how they do that over the next few slides. So, once the perf driver has converted the I/O request to the protocol blocks, the SCSI protocol, NVMe protocol, whatever, it hands it off to the SIM via the XPT. I said that earlier. It's a very basic mechanism, so it bears repeating. Once the SIM signals completion, it notifies up the stack that the I/O that the I/O is done. The transport layer passes the messages back and forth between the periph and the SIM, but it also enumerates the drives or the devices that are on a given SIM. It will answer some of the CCBs that are asking about information about the transport, how fast it is and so forth. It will answer those as well. I'll get into the probe device that the transport creates to enumerate devices in the system here in a little bit. SIM drivers. First of all, the S in SIM does not stand for SCSI. For a long time I thought it did, but I went back and looked at the original CAM standards and they said system interface module from the beginning. I thought that was a later thinking on your feet when ATA was added, but that was there from the start. So it accepts the protocol blocks from the peripheral driver, writes them to the adapter, and answers different questions about the drive that it has figured out. So how does the SIM get created? One of the mysteries to me when I was first starting out with this was, how do we get one of these going in the system? It attaches to the new bus device enumeration. In your attach routine, typically for new bus, or in a routine that gets called in a deferred manner, you create a dev queue with CAM SIM queue alloc. You create the SIM, and you pass it a couple of interesting things. You pass it the name, you pass it the dev queue you just created, and you also pass it a action routine for receiving CCBs that it'll deal with, and you give it a polling routine. The polling routine generally is only used when we're writing crash dumps because we don't have interrupts running and we need some way to pull the SIM to see if the CCBs are done yet. After you create the SIM, you need to register each bus that the SIM supports. These days, it's usually a one-for-one mapping. In the past, it's been many to one. So you do that with XBT bus register. And it goes off and it registers the bus and the global list that CAM maintains. And then that allows you to participate in device enumeration. You then create what's the CAM path for the device enumeration with XBT create path. But one of the things that I had to go looking for when I was preparing this talk was where does the XBT get created? That's something that's handled automatically in bus register. It associates the transport to the bus by asking the SIM what kind of bus it is. It sends a path inquiry CCB, it finds out what the type of bus it is, it sets up the function pointers to do that. In CAM right now, there's no per transport data, so it's just a function table pointer, a function pointer table that will map for all instances of a particular transport type. And that's handled automatically behind the scenes. You don't need to do anything special. So one of the areas that I had a lot of trouble understanding when I was working on the MDA driver was how do the peripherals instantiate? And so I thought I would spend a little bit of time in this talk going through that. When the path is created by the SIM driver that I mentioned a couple slides back, it sends out a path registered notification. The XBT drivers that have registered for this, the probe devices for the XBT drivers get a notification, and they kick off the whole process. In the early part of boot, when interrupts aren't enabled, the path registered get queued up and get released later once interrupts are running and the devices can be discovered. These path register notifications get turned into XBT bus scan CCDs that go to the transport layer, which kicks off everything. The transport layer runs a bit of a state machine to query the device. I'll get to the state machine and what it is in a little bit. But basically, the transport knows how to ask all the devices on the system, all the common information. So the SCSI transport knows how to do the inquiry command and maybe some auxiliary stuff to make sure the device is there and real, and fill in the internal data structures that the peripheral drivers will want to look at to see whether or not they want to claim this device. Similarly, for the ATA transport layer, it knows how to send, identify commands. NVMe knows how to get this information as well. The probe devices receive this information. Let me back up, sorry. Once the XBT probe device has finished its state machine, it will send an asynchronous message, AC found device. All the device perf drivers on the system that are listening for things will then take a look at the information that the transport has found and decide, yes, I can deal with this, or no, I can't. In the example I gave earlier where I had an SSD that attached, both of those drivers said, yes, I can deal with this. The pass-through device created an instance of itself, and the DA device created an instance of itself, so they could handle the stuff that they handle. The reason I have the pass-through device enabled in my system is the drives in that system generally are from vendors that wish that send us firmware updates as we find problems. And the pass-through device is what Can Control uses to update the device. Otherwise, I just read and write blocks off of it with the DA device. So why is the probe a complicated state machine? Primary reason is twofold. First, we can't block when you make a CCD request, it can't block waiting to complete. So the probe routine has to go, oh, I know that there's a device there. I need to send an inquiry command in the case of SCSI. Well, when it sends the inquiry command, it has to return right away. So it updates its state to a state that indicates it sent the inquiry command. When it completes, it knows, oh, I was in this state where I sent an inquiry command. I'll look at the inquiry command. And based on the details of that, it'll go to the next state. The state diagrams for the probe routines are a little bit complicated, so I'll go through a simple one and show you what at least my attempt at drawing SCSI resulted in. So that basically leads us to the second reason that the state machines are complicated is because the protocols are complicated. If you're doing domain validation, you have to do particular things in a particular order to make sure that you can get all the commands through. If you want to support tag queuing, you have to do particular things in a particular order. And the state machines deal with this. It gets particularly complicated when you have enclosures and power management and stuff. So you have to spin drives up or spin them down or turn enclosures on and off and do stuff that Ken can probably tell you a lot about. But I looked at that and thought that would make a bad example and went to the next one to find a good example for a state machine. So the one good example I found was the one I just wrote. And part of the reason for this is that the NVMe sim that I wrote, the NVMe drive, sorry, back up over the NVMe driver has callbacks for when it detects devices and so forth. So it does all the state machine stuff behind the scenes and then sends a notification, hey, I found it. So I was able to leverage that and have just a couple of states. We start off in the invalid state. The first thing we do when we get a bus scan is we go to the identify state. We look at the data that's present and do all the stuff to notify that devices are found. We wind up in the done state. If at any time during this a reset comes in, we go to the reset state, which just then immediately goes back to identify. We could probably skip the reset state, but when I was writing this, I didn't realize that the reset state and the identify state are really the same state. So I tried to draw the SCSI state machine. It wasn't completely successful. This is
You're missing a transition.
I was about to add a disclaimer that I'm sure I'm missing at least one. But do you know which one that is so I can add it? But you know, this shows the whole glory of it. There's no good tool to do this. But you know, it talks about TUR is test unit ready, it goes into inquiry. We see if it has ones or not, and we report all the ones and PPDs and get the serial number and do domain verification. And eventually, after you run the sausage roll backwards, you've figured out that you've got a device and you get to the done state. But I invite you to go read the code if you'd like to A, fact check me, or B, understand what's going on. And there's something similar for ATA. There are more states, and I couldn't fit that on the slide, so I'm not picking favorites here. I just chose this one as an example. So as I said earlier, when the perf driver is attaching, it gets the device found notification that is sent to everything. It has an async notifier. If you're looking at the NDA driver, it's NDA async. It finds the device that it gets and goes, oh, and asks the transport, oh, what kind of device is this? And it looks at some detail and says, yes, I can deal with that. So then it creates a CAM peripheral with CAM perif alloc, and it passes a number of routines into that. It passes a register routine, a start routine, and some more that I'll get to in a minute. Typically, the register routine is like an attach routine in NuBus. It allocates the SOSD, it initializes the IO scheduler. There's a whole bunch of stuff. I've listed them here, and I want a little bit of time at the end for questions. So, the interesting bits are that it registers an async event, async callback for interesting events that might happen on that bus, and then it calls XBT schedule to get things started. Nothing happens in CAM without a trip through XBT schedule. XBT schedule is what is the mechanism that the dev queue that I talked about earlier uses to make sure that transaction slots are happening. And I believe I have a slide on it a little bit later. Anyway, here's a list of the required routines that you need to create a walk device. They're pretty standard. Most of these come from the disk interface, which most people are familiar with. The interesting one, there are two here that are not part of the disk interface, though, that I'm going to call out. One is start, and that's called by XBT schedule when there's room for work. And the other is done. And you can have a different done routine for each request type. Most of the drivers in the tree just have one. And that gets called when the CCB has completed. So XBT schedule checks to see if there's room in the dev queue. If there is room, it allocates memory for the CCV and calls the peripheral start routine. The peripheral start routine goes, oh, I have a CCV, I can do work. Let me check any work queues that I have. In a couple minutes, I'll get to where those work queues actually come from. I have a nice picture here that I will talk to. The other thing that XBT schedule does is if there's any shared resources that are limited. So if I've got a SIM that can do 5 requests at a time, and we've got 10 drives attached to it, even though the drives can obviously do at least 1 IO at a time, CAN will only ever schedule 5 IOs in that case, because that's the limit of the SIM driver. A lot of these limitations are for older hardware, maybe less relevant today. I know Justin has advocated rewriting a lot of the scheduling to simplify it, to simplify memory allocation, and that discussion is an interesting discussion, but beyond the scope of this talk. So when you're doing IO, you create the CCV and call XBT action, and that pushes it down to the XBT or to the SIM. When the SIM is done with a CCV, it gets an interrupt, it sees that the IO is completed, it usually looks up in a mapping table that says, this cookie that I get an interrupt corresponds to this CCV, so I can complete it. That calls XBT done. XBT done also calls XBT schedule. And that's, you can wind up with really weird stack traces, particularly if you have bugs in your code, I'm told. So before the callback, the done callback finishes, your start callback happens. And that's so that we can overlap the IO in the SIM a little bit better. The other thing it can do, if there's an error, it can freeze the queue and re-queue IO so that they can be retried. The strategy routine is like most normal strategy routines. It gets BIOS from the upper layers and queues them using either the CAN IO scheduler or BioQ disk sort. And then it calls XBT schedule to maybe go do that item. So in CAN, everything gets queued once, and then it will get dequeued and executed. That's part of the inefficiency that we'll need to address if we want to handle high transaction rates for NVMe. It's one of the reasons I think Justin's idea of rewriting this layer is a useful one, because we can generally know if we can call the start routine immediately and bypass the strategy, perhaps. Drew?
So what is the transaction rate? I mean, the granularity of these messages is like max fizz in the best case, or is it like the disk block size? Or?
It's the size. It's somewhere in between those two. Drew asked, "What's the granularity of these messages? Is it max fizz? Is it a single disk block?" It's a single transaction. So usually, like for UFS, it might be 16K or 32K. If it's one of our systems doing a big read ahead, it could be as large as max fizz. So that's the size. Does that answer your question? Or?
You tens of thousands of requests a second.
Yeah, with 30 microseconds of latency, you wind up, I'm doing the math right in my head, with 30,000 IOs a second before you run into problems. But if you're doing 30,000 IOs a second, you're going to consume an entire core just to do that and do the CAN processing. In our systems, we're doing like 128K or 256K transactions, so the transaction rate isn't a big concern for us. A little bit of inefficiency is not a huge deal, although I know you want me to get rid of it because every little bit counts. But you know, that's this is a primary reason why Justin thinks that you don't need to call XBT schedule to schedule the I/O, which queues and dequeues. You can do it directly from the strategy routine. So the start routine, you have a CCV, you know you have a slot in the SIM to do I/O. So you fill it in and call XBT action, and then call XBT schedule at the end to see if you have another slot. Because sometimes multiple slots open up, multiple completions happen before you can get back to the system. Sometimes queues freeze, and when they thaw, you can get a bunch of stuff going on. This is also the place if you have complicated interaction between different types of I/O. In SATA I/O, for example, you can send a trim down, but it's not, doesn't participate in NCQ. So either you send a trim down, you can only send one trim down, or you send your I/O requests down that are NCQ, and the start routine enforces that restriction. And yes, there is a newer NCQ version of trim, but you know, a lot of drives don't support that yet, so we still need to have code to deal with that. And then the done routine, the NDA done, if you're looking at the source code, and it's called by the SIM as part of the XBT done processing. It also calls XBT schedule to see if there's a slot available. And like I said, you can get some interesting inversions because it calls it before it calls the done routine, or wrong point. The done routine sometimes also has to call XBT schedule because of the I/O restrictions. If I am doing a trim in SATA and it completes, I have to call XBT schedule because I want to unleash any read and write IOs that have come in and later on. And calling XBT schedule will kick it off. Everything gets clocked through XBT schedule. If you're writing a perf driver and it's hanging, it never hurts, except for performance sometimes, to call XBT schedule. There were several bugs that I had when I was writing NDA. I guess I do know something about bugs. There were several bugs that I had with NDA where I wasn't calling XBT schedule. And the I/O would happen, I would see that it was happening, and then it would never complete, and another one would never start. And that was because I had left out calls to XBT schedule. So here's the kind of a picture of everything that I've been talking about, where an I/O comes in at the top and the middle of this in the NDA strategy. So it queues the I/O to the disk queue and calls NDA schedule. NDA schedule is a wrapper around XBT schedule. If there are slots in the dev queue, XBT schedule calls NDA start, which then calls BIO queue first to get the BIO off of the queue. The BIO to CCB translation happens here as we pass it down. And then it goes all the way down to the hardware and comes back up, and we get back to our done routine, which calls NDA schedule, and then to make more things happen, or it calls BIO done to complete the I/O up the storage stack. So when you're writing a SIM, there are three routines that you need to write. SIM action is there to handle the CCBs. I talked about that. Again, there's the two types of CCBs, either the ones you queue to the device, it'll take a while to happen, or things you can immediately tell the XBT or the perf about the device. SIM pull is called when you've got a CCB outstanding in the dump routines. It's only used in dump, although it could potentially be used elsewhere. Right now, we only use it when we're dumping the system. When the system panics and we're taking a dump, we disable interrupts. I put that in for my 9-year-old. So when the system's writing out a crash note, interrupts are disabled, and we need someone to find that the I/O is completed so that we can write the next set of blocks. And then the SIM-IRQ is what completes everything up this stack, and calls it XBT dot. So the key points I hope people take away from this. These were some of the harder things that I had to learn, although the first one was easy to learn once I realized XBT means transport. SIM scans the bus for devices, either when it starts or part of path registered. The XBT probes the device by creating a special probe device, or probes the information about the device, creating a special probe device. These probe devices go through a state machine to get all the information and then tell the peripheral drivers with a AC device found. There may be many peripheral drivers that claim a single physical instance of hardware, which is BeagleBus can't do that. CAM can. And CCBs drive everything. If you don't know about CCBs, you're going to have a really rough time understanding the CAM code. And so I put this picture in to contrast with the picture at the beginning that had in the middle NVD and NVMe. This is what the I/O stack looks like with the NDA peripheral, where we've got all the, dang it, my slide's wrong. This NDA XBT should be NVMe XBT. But the layering is correct. So this is the different layering when you enable the NDA driver. I thought it might be interesting to, again, have another picture to see what's going on with this. And with that, I'd like to take any questions people have. Drew?
So, coming from a network guy, it looked like the NDA exports the multi-queue aspects of the NVMe controllers. And I'm wondering, it seems like, I may not have understood, but it seems like CAN is inherently sort of single queue. At least there's a single queue in the middle.
Yes.
I'm wondering how practical it would be to push the multi-queue aspect further up.
I'm glad you asked that. The person you're sitting next to, Scott Long, maybe you know each other. He's been working with me, mostly him though, on multi-queue extensions for CAM, so that instead of having a SIM queue or a dev queue, you can have one per CPU or one per CPU complex or whatever makes sense. And in that case, then all of the I/O wouldn't funnel through one data structure, which we all know from high core count experience is bad for performance. Each one could get their own, and they wouldn't contend on any locks to manipulate that data structure. So that's a very good thing, and hopefully next year Scott will present his talk on CAM multi-queue after doing the work and getting some phenomenal results.
Just curious, when you do BRQ disk sort, I was always conflicted about that. Do you need it for SSD or not?
Okay, so when I put disk sort up, that was an example of how you can schedule the I/O. The disk sort does the elevator algorithm, which you really need to do for spinning Rust. But for Flash, no, you just queue it as the first one or the last one, and then take it off.
Given the fact that we do a lot of cluster upper layers, probably does.
Right, and the DA, ADA, and NDA drivers, the NDA driver doesn't do any disk sort at all. The other two, if it's got a spinning rate of 0, which means it's as an SSD, it doesn't do any disk sort either. So, George.
So I started looking at some of the CAM entry and exit points. Is almost all of the work in CAM done at the boundary of those? Because that means we can apply dtrace without having to add statically defined trace points and start looking at latency.
Yes. Okay, so I'm sorry, my mistake. George was asking if he was looking at the CAM routine and noticed that a lot of the work seems to be done at the boundary points. And the answer is, I wanted to know if we could then exploit that to make it easier for instrumenting it with dtrace. And the answer is yes. CAM has, I didn't talk about it today, but CAM has a tracing routine that you can go through and see the CCDs going down and coming back up. And a lot of the code that's CAM debug, blah, 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 would be excellent candidates for dtrace. Most of it would be in CAM xpt.c, although you would probably need a couple in each of the individual transports, the ATA XPT and the NVMe XPT as well, to make that happen. But it would not be a ton of work to make that happen.
How much more overhead comes out of NVIDIA?
Right now, so let me repeat the question. Alexandra wanted to know what the overhead of the NVD versus NDA. Right now, NVD does things unmapped, and the NDA driver still has a bug where it thinks it can't do unmapped I/O. So with NVD, we see maybe 85 gigabits a second, gigabits a second in our 100G machines. And with NDA, what were the best numbers? 65, 75?
The best was 65, but it wasn't stable because the latency spikes kept going up and down.
Right. So because of contention in the VMware, we would get large latency spikes, so the control plane would slow down traffic to our system, so it was hard to see what the best peak you could get. But right now, there's a little bit of a performance difference because it doesn't do unmapped I/O. And the 80 gigabits is off of 4 drives, 4 lanes, PCIe 4, so it's pretty close to line rate. Yes,
I had a question about the state machine for enumerating disks you showed. So this is it's an asynchronous callback-driven state machine?
Okay, so yes. So the question was, is the state machine asynchronously callback driven? And the answer is yes.
And have you thought about making it synchronous, like one thread per enumeration to simplify it? So you don't leave reference counts and such?
I don't know if anybody's thought of doing that. One of the things with CAM is all of this happens in parallel anyway. We can start this device and this device and this device and send all those requests down to the SIM. And as they complete, it goes to the next one. So we don't, unlike NuBus, which has one synchronous thread to enumerate everything and you have to wait for the next thing to come in. CAM's enumeration model allows all of that to proceed in parallel across the multiple SIMs and drives, buses and everything. It can happen in parallel so that you don't have to wait for that. Yes, Justin, the other Justin.
Yes, the other Justin. When I was writing the SATA driver for PowerPC, SSC, I copied HCI and I noticed that it had to complete the CCDs with innocent, marking as innocent when errors occur. Complete all the ones that didn't error as innocent. But I thought what you just said that CAM knows enough to when you freeze a queue, it knows enough to restart everything. So would it just pulling out the erroring CCDs be sufficient?
Okay, so to briefly repeat the question, when HCI reads the CCD, it marks it as innocent? Wait.
It marks if an error occurs. So if there's an error if there's an erroring CCD, it has to marks all the others as innocent and completes.
Oh, right, okay, so, so when the HCI is completing the I/O, if it gets an error, it marks all the others as async. Because when an error does occur with SATA, automatically all the other requests are considered to have not happened, and will return errors back. And so that reflects that. I think I'll have to talk with you afterwards for the details, or you can talk with Alexander, who wrote that code originally. He's sitting 2 people down from you to resolve that. But I think that's a little bit more detail than I can go into up here. Last question. Yes.
So I'm just asking a question for somebody on IRC, our Ocala. He wants to know if CAM has anything to print the tree similar to the syscontrol's kerm.geom.conf or syscontrol kerm.geom.conf XML.
Okay, so the question was, can you print the CAM tree similar to the geom methods that we have? And there's a CAM control dev list which will list the devices, but I don't think we have anything that will print that in tree form. Ken or Scott or Justin, do we?
No, and I think from a tree standpoint, it would be very difficult to get additional topology information. You know, for the most part, you get a linear list from the HPA. So what you already have in the CAM control dev list is about all you're going to be able to get without really digging down into the SAS or fiber channel or whatever topology you have.
Okay. Just to repeat your answer since you're not mic'd, Ken said no, there's not. And he's doubtful that there would be additional useful information apart from the linear list, because CAM tends to be bus, here's the things on the bus. And there's not much more of a tree beyond that. And you would need to dig down into the specific details of fiber channel or SCSI to find more complicated topologies to look at, and look at enclosures and that. Okay, I think we're done with time. So if you have any other questions, come see me. Thank you very much. That's what people say sometimes when the system crashes. Because all of us inside love to chat our inner 9-year-old. Well, that's one concept.
Yeah, they kept saying so. I think the X-Land data. So we get this one, I think. Just one other about the smart. Exactly, yeah, that's exactly.
Yeah, thank you for. Yeah. So I did actually look at but it shows up yeah, it's
Work on slides, man, work on slides, not on updating boards.
Yeah, so trim's causing a stack up.
Or am I just procrastinating? Procrastinating. No, but I'm putting off the delay.
Oh, okay, yeah.
I'm not doing
How do you
Trims are now becoming unviewable. Yeah. That's really complicated stuff again. Some of the early drivers, you know,
do IOs for us, which is very important. The S.M.A.R.T, for those who don't know, is a self-monitoring and reporting technology that was added sometime around ATA version 3. And this is kind of what it goes like if you're going to try to talk S.M.A.R.T with the drive. You kind of go out and go, how are you doing, drive? And it comes back and spits a bunch of garbage at you. For the most part, it's a large table with a bunch of different values that some of them are not guaranteed to be consistent across the different vendors. The more formatted version of that data looks like a table that we have some strings to that give us thresholds that are numbers that if we're actually below it, it indicates we have a problem. And that value needs to be scaled by some f of x to get to what that value is. It's not real clear what f of x may be for a different vendor's drive, and how fast are we approaching the problem that S.M.A.R.T's trying to tell us about. The most common thing that people use today to look at S.M.A.R.T data is the S.M.A.R.T bound tool package. It's very good at reading these outputs and formatting them in at least a human readable form. There is an ATA control utility that exists in OpenBSD and NetBSD that does much of the same thing. I don't know that these tools have any type of long-term monitoring daemon like S.M.A.R.T Monitor Tools does. Everybody that's interested in S.M.A.R.T data is pretty much using S.M.A.R.T Monitor Tools. It's available on all the platforms, just like GROF is. It's used everywhere. But are we doing that voluntarily? Is it something that we really, I mean, it's one of the only things out there, so is it the only choice in the market? And it has some definite advantages. It's available on all the operating systems, like I said. It supports the SCSI drives. It supports SATA drives. It has a huge table of vendor-specific data. I wouldn't want to recreate that data by collecting it from the hardware vendors. It has the smart monitoring daemon that I mentioned, and it has the ability to implement some commands that are basic and or longer term hard drive testing commands. Basically, is what I'm talking about there for those that know S.M.A.R.T are the short drive test and the long drive test. And it's, of course, it's familiar by widespread use. Everybody's using it. It also has some disadvantages. One of these came up during almost lost that. The developer summit, and we're trying to move away from GPL code. Actually, I believe, a target goal for version 12 of FreeBSD to eliminate the GPL code in the base. S.M.A.R.T Tools is a GPL utility, so we're not going to be importing that. It has limited formatting outputs that basically you can't really change the way S.M.A.R.T talks to you. You might stick it through Opera, grep, or SAD and do something with it, but you're basically stuck with the CAN text output. It isn't a library. Like I said, you're going to call the utility and get a textual output. It didn't have support for NVMe as about 3 or 4 weeks ago. That's been added, so they can actually deal with the NVMe drives now. The acoustic management commands and some of the security commands are not supported by SMART-Mon. I don't know if you can do a secure erase using SMART-Mon. For some people, that's a pretty important access that you need to get to. It doesn't, you don't have direct ability to deal with storage bus operations, and that's more of a CAM control. It used to be ATA control, but we don't have that anymore, type layer issue. It doesn't support the eject command for CD-ROM drive and some other stuff. And it doesn't have test unit ready for SCSI devices, which you might want in scripting to make sure your unit's ready before you go blast some commands at it. It doesn't support raw CCBs. That's available through CAM control, yeah. And it doesn't have anything to do with virtual disk, and that's, well, why do you even want to talk about SMART over virtual disk? We'll get into that a little later in the talk. There's some environments where you may actually want to be able to access SMART through a virtual layer. The ATA control utility that exists in some of the other BSDs, it's, of course, has a BSD license on it, so it's readily usable. It has support for the acoustic management commands, which are pretty universal from my understanding. It can terminate the simple and the extended SMART test, and it has support for the SMART security features. Like I said, it's not per se a SMART feature, but the secure erase is supported. And it has support to turn on the write cache on the drive, which is not available in SMART, or in SMART-Mon tools. It has a lot of disadvantages as well. It was removed from the FreeBSD system. It was deprecated, I believe, along with bringing the CAM. Caused some issues there that the ATA controller was, or ATA control was doing things that were not healthy to the way that CAM was trying to operate, making it difficult to try and bring that code forward. It doesn't have any information about the vendor-specific stuff that's going on in the drives, which unfortunately is a hard problem. It's a huge amount of data. It doesn't have any. It didn't have any way to output different formats. It wasn't a library. It was just a statically linked executable. It doesn't have any support for NVMe, of course, because it was deprecated before we had even an NVMe driver. At the present time, I don't know if the NetBSD or OpenBSD projects have added NVMe support to it. That may be coming. It doesn't have support for SCSI test unit ready. It doesn't have the ability to deal with control blocks. And it, I looked at some of the different versions of ATA control, and it was actually trying to issue SMART commands before validating that the drive was capable of doing SMART. And so that's just really a bug in the code that needs to be addressed and fixed. So the expansion of GROF was caused by Mandoc, and kind of everybody uses this everywhere. So Michael's idea here is that we build a similar solution to be used by everybody for the SMART layer of hard drives. Mainly because the current environment is the disadvantages are way, way outweighing what we have for advantages. This started evidently with a tweet between him and Gil Nguyen and OpenBSD, and he asked if a certain tool could do this, and the result was that it actually could. So that was where Michael decided to start down this walk. So we put down the keyboard, we reached out and asked what the requirements would be for doing this. And one of the first ones that came up was, well, we need an open source tool that has some friendly license on it, so we can get away from the SMART-Mon. wanted to fix the limited output of it that was available from the current tools by adding an extensible framework that would allow us to output information in hex, human readable form, JSON, XML, whatever you want, shell variables if you're trying to script some stuff in shell. ZFS does a very good job of this. Its interface is in a way that it makes it easy to use it in other tools when you're getting statistics out of ZFS. So if we can, we want to make it a library. ZFS's statistical interface is built as a library so that you can easily route tools around it. Looks like I got a sequence here. There's an additional item here about how do you recognize if one of the things SMART tries to do is use scan for devices. Well, in implementing something like that, how do we reliably recognize whether we're talking to a HEA drive, a SCSI disk, or an NVMe? Because the way that you deal with errors and or SMART type stuff with those drives is very different. It doesn't make it trivial. And simply leaving yourself with a manual override. The inability to deliver raw command and control blocks, we can do that with CAM control, and that was the right thing to do. This is how you speak SMART to a HEA disk using CAM control, using raw control blocks. It's not very pretty, it's pretty painful. If you get a bit or a byte wrong somewhere, you have a pretty serious problem. Fortunately, the worst one is secure erase, and you're not likely to hit that.
There's others that'll.
Go ahead, Mark.
There are others that'll screw you up just as bad as secure erase.
Well, there's definitely some that can put the drive offline for a long enough time that if it were a critical file system, it would cause you some grief. Evidently, John Baldwin asked some things about, well, why not use something like a CCB dump, just like TCP dump does, so that we can look at the raw CCBs going around down to the bottom layers of CAM. Some interesting data can be gleaned from that way. You're not going to get SMART data because currently there isn't anything that's passing SMART CCBs around, it's asking the drive to do that. And the other one was if we do something like that, like TCP dump, is how do you do the filtering on whether you're doing a read request or write request, whether you're doing some other weird things. And Warner could probably tell me more about that because we've been playing in the CAM lab recently.
Just a little.
The inability to support virtual disk. Well, why would you even want to support a virtual disk? I mean, you're supposed to be presented a virtual machine with a perfect disk that doesn't have any flaws on it, that's going to have really good performance, supposedly. Well, what if you're using a cloud provider and you want to know if his disk backing store is really providing what you're paying for? And are there any ways to modify the virtualization driver layer? We're talking about para-virtualization here, to get something like SMART or even get SMART data through it. The other one that comes up is what about the home lab environment where I'm building a machine that is dealing through a virtual layer and talking to a physical hard drive, and I'm trying to do hard drive diagnostics, or I'm trying to develop hard drive tools, or I'm trying to write something like SMART on in a virtualized environment. And I can't talk SMART to the hard drive anymore because the virtualization gets in my way. So there's some interest in implementing some things there. What does SMART look like? Beehive currently, if you try and pass SMART through it, it's not going to give you anything. It's going to give you a perfect drive that has no SMART data behind it. And do we give it synthetic values? Do we give it some statistics about the backing store? These are all questions that people are going to need to answer. I don't have the answers for them. Do we give it the worst status of all the devices, the worst status of any device? And what about pool redundancy? If there's a drive behind the pool that's got bad SMART data, do we really care if it's in a redundant pool? It's not going to affect us. What about collecting large amounts of data? How are you going to deal with trying to deal with smart data from 90, 100, 900 drives? Are you going to cache it? Are you going to send it? Are you going to send it to syslog? Are you going to use some external logging tools to analyze that data? Do you think it's about somebody like Yahoo or Google or any of those people that have huge arrays? What are they doing with their smart data? What can be done with it? There's some other ways to deal with hard drive failures and errors that don't even involve SMART. Looking at controller resets compared to the host, the number of times that the host resets, and you look to see if you have odd rates there. Might be one way to collect some data. Hopefully those two stay one-to-one. And what can we detect today with in-base tools? There's some stuff that I can believe you can do with dtrace to look at hard drive latencies. And if you're seeing a sudden escalation in hard drive latencies, you can presume that the drive is probably either remapping sectors or having problems reading those specific sectors. That's interesting data. From SMART, you can get things like service hours. Most of the vendors, I think, are getting more extremely consistent on what they report for how long the drive's been running, power on hours. Temperatures, there's more than one temperature that you get from most drives. You get some historical data. I forgot to bring with me today, but I have a drive that actually has a failed in pass condition that was caused by a historical high temperature. The drives are recording that type of data is available to us. What do you do with that data? I'm not sure. I mean, if a drive failed in the past, is it important to me today? Type thing. The reallocated and pending sector counts are probably the two most interesting SMART data that people want to look at. These, the reallocated sector counts gives you an indication of how much the drive has had to relocate sectors because it has some problem reading or writing to a specific area. The pending count is another very interesting one because it's by design, it should, if it finds a spot it doesn't like on the drive, it says, okay, this is pending until I can read the data from it. And supposedly, if you successfully read the data from it, a remap operation will occur and the pending count will go down. Well, and SMART doesn't always do that for us, but watching the pending count can be a good indicator that the drive may be starting to develop a problem. The latency climb I talked about just a minute ago, frequently when you see that, you've got maybe 8 hours to react. You may have as short as 1 hour to react. You may have a lifetime to react because it may be a transient condition that's not anything to do with the hard drive having long-term storage issues. There's a YouTube video out there of somebody screaming into an array full of hard drives that drives the drive latency through the roof. That's caused by vibration. Drive's just fine. It's just trying to deal with the fact that at 7 micron distances between cylinders, just a little bit of vibration causes head tracking issues. And so you may get data from a drive that is actually meaningless as far as long-term failures go. The current, like I said, I believe dtrace can detect the latency climb. I think there was actually some one-liner scripts or short scripts that can collect data. I think Warner did some of the scheduling stuff collect extensive latency data on region drives through the.
Yes, the IO schedule will keep a moving average of the latency recently for the requests.
Per device.
Per device. You can also use GStat to get average latency information. Dtrace is good if you want to look for outliers.
Yeah, okay.
And that's, outliers are what you care about.
Right, yeah, that's the indication that your latency is climbing. And with that data is what you're trying to do is predict failure. That's what SMART's about, is trying to hopefully predict the drive failure before it becomes a critical failure. So that you can schedule maintenance and hopefully fix it. This is we're not attached to the disk control name, it's just a proposal. This is a proposal of some of the types of commands that would be implemented. Getting the smart data table, which is the main amount of information you want out of it, turning the LED on and off so you can identify what drive it is that you're getting that data from. The ability to issue a raw command control block like CAM control does, or raw CCB like CAM control does. The ability to possibly to turn on the device's TCP dump-like functionality, because I don't think you want to have that on all the time. But to be able to turn that on so that you can start reading CCBs from a TCP card. I guess it would be a CCP dump utility. Get reset counts, eject the drive, which is currently a hard thing to do. The next steps are what are the pain points for the current developer community and the user community that has to do with SMART. I mean, where are we seeing problems? What are the current strategies being used to deal with hard drive failure and to deal with SMART in itself? And what your feedbacks are, and what your encouragements are for this group that's working on this to go forward with. And thank you. Are there any questions? Great.
So what is the state of the software at this point?
The man page.
The man page, okay.
We need a lot more feedback from the developer community and the user community and what they would like to see in the tool. Basically, we're trying to replace the functionality that SMART is providing without the GPL license. It's really the target. And to get something that we can include in base. Yes.
You mentioned earlier about SmartOn's huge database of vendor information. Is there any thought about how we're going to deal with, because we can't just copy that since it's GPL, right?
Correct.
So how we're going to deal with that aspect of it, because that's a pretty difficult.
Right. A large amount of that data is device-specific quirks, and that you have to do some odd things to certain devices. Yeah. Fortunately, a large amount of that are legacy devices. So some of it, we may be able to greatly reduce the workload by going, look, we're only going to take and deal with data about ATA 7 or newer devices. And that, you don't have to deal with a huge amount of devices. And by ATA 7 or 8, the specifications and how vendors were doing it became clear enough that the amount of the data that's created for that problem is much smaller.
Okay.
Most of it has to deal with vendor-specific cable entries in the SmartOn data, and then especially with the SSDs and now the NVMs, as there are a million new parameters. NVM is actually going to make that table grow, and the need for it to grow because different vendors are going to report different things about how well the drive is doing on lifetime. The solid-state drives have much more data in that area about how many times I've rewritten certain blocks, and those blocks are getting close to their end of life. But I suspect that we can downsize that data.
Okay.
It means some drops of legacy support. Yeah.
Integration with ZFS, so ZFS would know this drive's about to fail. ZFSD would take it offline. Is that
right? Yeah, that's in there. It hasn't specifically been addressed. We all know that doing things behind ZFS back is a very bad idea. What occurs now is the controller layer on a failing drive can cause a retry issue, and the drive may take a long time for ZFS to recognize that it's gone. SMART may be able to provide, if ZFS can be taught about SMART and how to get SMART data, it may be able to proactively go, this drive is getting bad, let's get it out of the pool.
Go ahead and throw it in a hotspot.
Go ahead and throw it out and bring in the new hotspot support that's been added, which would be really, really proactive. Warner.
Yeah, one problem with proactively removing drives or pulling SMART data is that SMART data is not NCQ compatible. So you have to stop all the other I/O, get your smart data, do the I/O again. So when you do that, some workloads that introduces too much latency. We pull smart data and Netflix like once a day to avoid interfering with the video streaming that we're doing.
Yes, that's a very serious problem. I'm not advocating that we go look at smart data anything more than maybe once a day. And the other thing would be to use some of the more proactive, non-smart type data collection to decide if ZFS should take a drive offline, particularly the latency response of the drive, or use that to trigger a probe for, has the smart data changed? Is the drive seeing something going on?
At IX Systems, we probe a hell of a lot of smart data, and in certain cases, I don't know if you have any insight into this, smart CTL-X, the deep probe, can actually hang the controller of spindles. We've seen this a couple times, and it's terrifying because it means your debug script has just trashed your debug.
I don't have an insight as to what's going on there without looking at the specific instance. I have some ideas about what might be occurring. But,
like the A flag works fine, but the extended, the X flag, like digs a little too deep, and the controller goes off the deep end.
Yes. Anyone else? Yes.
So for the particular CCD dump instance, so I have a particular way to do that. I mean, using filter drivers for the CAM and the hardware driver. So I'm going to have a discussion about it in the Dev Summit track at 2 o'clock, 2:45. So
okay, so
I welcome people to like join that and like give your input on that, and any ideas can be like discussed there. So
yeah, I'll get with you, and I would like to see what you've done. So you have implemented a CCB dump.
yeah, kind of, yeah, exactly. So
Are
using a filter driver for the CAM.
Okay.
So that you can actually access the CCD and then all the fields in the CCD. And so I had actually written it to simulate disk errors initially by changing the fields in the CCD. So that way you can have access to the CCD and
real good way to test the ZFS.
Yeah, exactly.
Failover mechanism.
Yeah, yeah. So that was one of the test cases I actually wanted to test, like failovers and switchovers. So yeah, I'm going to have a discussion. So people are welcome and give your input.
What time today?
It's at 2:45 and 1130.
Okay.
So, yeah.
Am I done? I can quit listening to an echo. If I keep moving, I find a better spot.
Well, they tell us that they don't mind this. That they don't mind us using the term. Well, this would be fun.
Very long. I guess. My time is
110 years.
I wasn't nervous. You didn't go very well.
No.
Are you one of your right line?
We see how we right now.
I just want to test my video.
Hey, Greg.
What did I just hit?
You actually did a half hour, 4
And it
minutes.
just starts my, wow, it's so much easier. Why didn't anybody tell me?
be right on. Yeah. Sorry. Time. Get up your road here.
So my name is Ruslan Bukin. I'm working in the DARPA chair project at University of Cambridge Computer Laboratory. And my last project is FreeBSD 5. And so we have supported new architecture in FreeBSD called RISC-V. And I just have a few slides about it. So the first question people asking is why RISC-V? Why we need that? And the answer is actually very obvious, that all of the popular architectures are commercial, and that means that you can't just take it and use it in your project. You have to get a license first from the owner of architecture, and this is sometimes impossible. For example, if you run some project in university or creating some commercial company and you want to use some architecture, you have to get license and pay for architecture, and you have to be big enough to use architecture, commercial architectures. And while RISC-V is the first completely open and BSD licensed architecture created in the University of California, Berkeley, they started to work on that 5 years ago, and finally they have something that works. And with commercial ethos, there is another problem that most of them are popular in certain applications. For example, if you're creating some mobile project, you probably will need to use ARM and have no any other choice, because ARM is popular and created for mobile applications, while for servers you have to use Intel most likely. And RISC-V is an extensible architecture. It allows to create extensions easily. Actually, there will be talk from Aaron Thomas tomorrow about RISC-V. My talk is mostly about porting process. So, and RISC-V has a few instruction set architecture, a few instruction sets. It is RV32G for general purpose computing, and RV64G, and one for embedded applications. And have a bunch of extensions. For example, C compressed extensions allow it to compress code twice, and some other extensions. So, unlike MIPS, RISC-V has no branch delay slot, which is good, and unlike ARM, it has no conditional flags, which I found also very nice. And it is a little angel architecture, and branch offsets are related to program counter, which is also modern way, unlike MIPS that has offsets. Offsets starts from the beginning of kernel, and RISC-V has 4-level page tables and 4 privilege levels, and the instruction length is 4 bytes and 2 bytes for compressed extensions. So it has 4 privilege levels, and only one is mandatory, is machine mode. Hypervisor mode is not, specification for hypervisor mode is not released yet. So we use in FreeBSD 3 privilege levels: machine mode, supervisor mode, and user mode. And machine mode is designed for firmware for vendors. We using that in FreeBSD, but we should remove someday a machine mode split off machine mode from FreeBSD, and we need to create some bootloader maybe for that. So, why to use the FreeBSD and FreeBSD RISC-V project? Again, BSD license gave us a completely fully BSD licensed hardware software stack. RISC-V BSD licensed, FreeBSD BSD licensed, and LVM Clang. Also MIT or BSD licensed, something like that. That gives us an easiest technology transition, so we can freely distribute our code and machine code and software code. So FreeBSD RISC-V was based, a port for FreeBSD was based on RVA port. So what I started initially is I just copy-pasted everything from sys ARM v8 to sys RISC-V, commented everything that has not passed compilation, almost everything machine-dependent code from ARM, and starting implementing RISC-V machine-dependent bits. And it took for me about 6 months from scratch with people who helped with that. They all listed here: Robert Watson, Dan Langille from University of Cambridge, and Turner, Aaron Thomas, and Edmund Steve from Foundation. Thanks to them. So project started 1 year ago, in August 2015, and in October we already have a kernel that works, that has booted until mount root prompt. It has lack of PMAP bits because most of PMAP machine-dependent code will be needed later when we do a breakup of user space. So it took another couple of months to implement more machine-dependent code for PMAP to get user land working. And in January we already started to commit everything to FreeBSDCan. So it takes just half a year to bring up new architecture, which is really, really great. And we was working on SMP in February, kernel debugger support in March, trace in April, and we now have modular support committed to FreeBSD, which is really good. So RISC-V has a bunch of simulations. There is no complete silicon yet, stamped yet. There are only simulation and emulation tools. For example, Spike is a simulation from University of California, Berkeley, brought in C++. It is the best simulation tool I ever used. It allows us to run instructions step by step, which is really, really important when you do porting FreeBSD to new architecture. QEMU probably should also have this feature, but I haven't found it. And the only hardware implementations done in a Chisel language and simulated on FPGA. It is a Rocket Core implementation by University of California, Berkeley, and the fork from Rocket Core, Low Risk, is a project in the University of Cambridge. Actually, one of the founders of Low Risk created Raspberry Pi as well. There is some problem with Low Risk. They forked FreeBSD a year ago, and there was a critical patches already committed to Rocket Core since then, and we are waiting a Low Risk when they merge from Rocket Core these patches, so we also will be able to run FreeBSD on that. This is a board. We can run FreeBSD RISC-V already, and it works very good. It is that board, heterogeneous board with FPGA core and ARM core. So we run Linux or FreeBSD on ARM core, and we burn a bit file from Linux to FPGA core and loading FreeBSD RISC-V from FPGA from inside Linux of FreeBSD running on ARM core. It is Rocket ship is a 6-stage single issue in-order pipeline, and it is written on Chisel language, which is based on Scala language. And first of all, we need to generate Verilog from that. And after that, using Xilinx tools, we are getting bit file. Low-risk guys using a different board, more cheapest single FPGA core board, Nexus 4. I actually more like heterogeneous boards, which is easiest for us to upload the image from working operating system that runs on ARM or Linux operating system. And low-risk guys promised to create a first silicon next year. We'll see if they fit this amount of time. So when I started porting FreeBSD to RISC-V, we had to work on standard things like first assembly code. It should do reset some configuration, puts hardware to some known state, and enable some interrupts, and creating some machine-dependent stuff. In the RISC-V, there is a machine mode, and all the interrupts happens in machine mode, and we can't disable interrupts in machine mode, so we have to store the information about events somewhere. So we have to build some read buffer for that, and we will read these events later in FreeBSD once we switch back to supervisor mode. So we have to handle all the interrupts in machine mode. And once we build this, we need to do some other stuff, like build initial page table so we can call C code and enable new and stuff like that. And the first thing we need to do reporting is the console, obviously. And RISC-V has its own HDF bus that has a console device and also block device, and also the net device. And of course, another first thing we need is atomic functions. It is really, really important to implement all the atomic functions initially and test them. My problem was that I have implemented that but not tested well, and it was really, really hard to find issues in when FreeBSD boots issues with atomic functions and other problems. We need to provide like physical memory regions and work on initial code for PMAP, mostly PMAP bootstrapping. Like a few functions in PMAP that bootstrap enough memory to run FreeBSD. And then we need to work on exceptions, context switching, and implement functions like fork trampoline, machine-dependent functions. And we need to work on devices, device drivers for timer, interrupt control driver, and device drivers. We need to implement event timer and periodic timers for FreeBSD. And once we go into user space, there is a bunch of functions we have to implement to copy data between kernel and user space, like if you byte, SU byte, and other functions. And once we have all of this done, we already can try to run some statically linked applications like bin shell. And signals most likely is the last thing we need. Even bin shell don't require signals, so bin C shell I think requires signals. So if you want to run C shell, then we need signals implemented. Yeah, as I said, all of the traps happens in machine mode, so we want, and this is a single vector, so we get in a trap and looking at the registers, see what the trap comes from. And once we get some information about that, we switching, redirecting the trap to supervisor. And in supervisor we have two vectors for supervisor exceptions and for user exceptions. And there is some very easy assembly code for that. In case of user exceptions, we need to do some additional stuff like storing stack pointer to scratch register. Exchange a stack pointer from user space to kernel one, so we can run kernel on the kernel's stack pointer, not with the user stack pointer. And the most hard things during reporting was PMAP, obviously, and there is a bunch of functions, about 40 machine-dependent functions we have to implement. Functions that manipulate page tables, like creating page tables, removing, and functions invalidating cache, protecting some regions for copy on write things, and stuff like that. And once we have implemented most of this, we can try to run user space. In user space, the first thing we need is to compile gmalloc memory allocator. There is lots of defines and parameters and stuff like that. And of course, C startup code is also important. The code that will be embedded to each binary, user space binary, we have to implement, and some bunch of libc code like syscalls, set jump, long jump, set thread pointer, and we have to. I have disabled FPU because we have not yet implemented FPU. We use soft floating, so we have to compile some as well. And runtime linker is the second most hard things that was during reporting. So everything was committed already. The first three things was committed last year, and other support was committed in January. Yeah, and concluding this all, I would like to say that PMAP and runtime linker was the hard things you important, especially when you work on both runtime linker and PMAP. This take like a couple of months probably just to understand what's happening and how to fix that. Another problem, this problem already is with hardware, that hardware has only a single page table base registers for both user space page tables and kernel page tables, and this was a problem because we have to switch page tables once we switch in the process, and once we switch page tables from supervisor mode from a kernel to user space one, we already can't use the kernel functions. So we have to do that like at the last step before we switch into user space, and it is impossible. So we have to implement like a shared page table support. So we share first level of page tables between kernel space and user space, same way actually as RISC-V do. And I think this is not a modern way to implement to make a hardware. Best way is if your hardware has both two page table base registers for supervisor mode and for user space mode. And RB8 has two registers, which is really good. Another problem is that it has only one single scratch register. So once we switch from a kernel to user mode, we have to store somewhere a stack pointer so we can use it when we return back. And we also have to store somewhere a per CPU pointer in case we're running SMP. So having one single scratch register, we can't store both of registers to this one, to this temporary register. So we have to do some tricky things like storing per CPU pointer on stack, and then we store a stack on a scratch register. And this was like a painful work for me. And of course, RISC-V is a new architecture and has lack of documentation. Actually, has none of documentation for runtime linker, for example. So this was a problem as well. And while we have fully working FreeBSD, we of course have more things to do this year and next year. And first of all, we need to update ISA instructions. So here already changed a bit. They have changed the format of some instructions. So we need to work on that. And we need to work on generic kernel. We're using these days flattened device tree, statically embedded to the kernel, because RISC-V has some plans to implement their own way to. They plan to provide their own description of hardware, so there is none of work done yet in that area. And we have to use something like flattened device tree embedded to the kernel, so we can't have general kernel right now, because different implementation has a different amount of memory, for example, and different set of devices, and hardware still do not provide the information about that. They plan to use some description language they have not wrote yet. And we need ports and packages for toolchain to create this, so people can test it easily, just taking the port and can compile FreeBSD. And also would be nice to have QEMU integration for ports, so we can run a cross compilation of QEMU package, for packages in QEMU. And as I said already, we need to split off a machine code that we have in FreeBSD, because the machine mode intended to use in firmware. And FPU has not yet implemented. I plan to work on that soon. And LLVM clang is not ready yet. There are some bits of implementation done, but it is not fully done, and we can't use clang yet. Actually, RISC-V is still evolving, and they change it every day. Significant things, so maybe it will be hard to support both GCC and clang for them, so we just wait. Then final specification will be released, and maybe someday someone will give us a clang support. The RISC-V has 32-bit version, and it is really nice for some embedded applications, so maybe we also need to work on a 32-bit version of kernel, our kernel 64-bit. As I know, there are none of counters yet available in hardware, so nothing to work on that area yet. And we plan to work on some additional devices for HDR bus that is used by RISC-V, like Ethernet. Yeah, that's it. As I said, Antonis will give probably a more complete information about RISC-V tomorrow. Yeah. Any questions?
You mentioned the scratch register. Can you explain what it is and what you need to use it for? Why it's a problem? Is any one of them?
Yeah, so the problem that we have to store a stack pointer somewhere once we switch into user space.
Okay, so you need to hold on to the user mode stack pointer while you do this.
We have only one stack pointer registers for both kernel and user space. So once we switch stack pointer to user one, we have to switch it back once we return from user space to kernel mode, and we just no idea where to get it from.
Okay.
So we have some like scratch registers, and we store stack pointers to scratch register.
Gotcha.
And same problem with per CPU pointer, because if we run symmetric multiprocessing kernel, then we have a per CPU pointer for each core. And we also have to store it somewhere, so once we return, because we're using thread pointer register for that, while thread pointer registers is also used in user space.
Yes, yes.
Yeah, so we have to store our PSP pointer somewhere, so we can use set it to thread pointer as again once we return back. So we store it first to stack pointer, and we store the stack pointer to scratch register, and we go to user space.
I think I prefer the old approach of having a few shadow registers that aren't shared with user space. I can see why this is going to be an issue.
For AV64, there's no equivalent of KGS base, and it doesn't implicitly switch stacks on transitions. You have to manually do that.
I have a small question. You said the platform is evolving. Are you guys talking to the authors of this ISA?
Yeah. We are in touch with them, and we always. I was in January and still RISC-V workshop, and will be on 4th RISC-V workshop in a month in Boston. And yeah, we're totally discussing things, and of course, I'm working in a computer laboratory, and the low risk guys sitting upstairs, so we chatting with them as well.
Okay.
And
maybe it's the first time in history that FreeBSD can actually give some feedback to the emerging platform.
yeah, and BSD family also comes from Berkeley, I think, right? Berkeley University. And so they are interested as well in FreeBSD support. Yeah.
So I guess some of the challenges that you mentioned might be resolved in some future revisions, right?
What the challenge?
I mean, for the registers in some of those applications.
Actually, it's not a problem. It is okay. Everything. It just gives us like a bit tricky code that may be hard to read, hard to understand for some beginners. But in general, it works okay. And the reason they have no additional registers and they don't like to add more registers is because if they add registers, hard drive will be bigger, and they will need bigger ASICs, and it takes more money and stuff.
Yeah, it's always trade-offs.
Yeah. But low risk are more, how to say, they said me that we can add as much registers as we want.
Yeah, but then they end up forking the ISA. Yeah. And part of RISC-V, it seems a lot of people want to take them and use it as a model for building little cores and FPGAs and hardware. Not necessarily just purely for like building ASICs for children to solve.
Yeah, I mean, so the way RISC-V is set up is they have a small base ISA and they expect people to have extensions on top of that.
Right.
So they have standard extensions, they have non-standard extensions. The low-risk guys have their own extensions for I/O and security and things like that. So they're able to layer things on top of that as long as they meet base ISA specifications.
But like an additional scratch register for transitions would be like an extension to the supervisor mode.
So you can do that if you want.
Yeah, but it wouldn't.
Yeah.
There's no guarantee that everyone would implement it.
No, probably not.
So.
Yeah. But yeah, they were setting up a kind of standardization process for standard extensions.
No, the only question I got, when do we get the hardware?
When?
You know, like hardware that you can buy, like Raspberry Pi things.
Yeah, so low risk guys plan to provide not just silicon, but the board as well, like same as Raspberry Pi, and one of the founders of Raspberry Pi working on low risk, and they plan to provide fully open source with hardware software solution with fully open source schematics and fully open source chip. Yeah, as I said, they will plan to stamp silicon next year. Honestly, I don't believe it happens next year. But who knows?
Yeah, so Berkeley has a bunch of these test chips. So they've done like 11 or 12 like ASIC runs, but those are just like internal, so it's not something you can buy. But yeah, the low risk guys are probably the first ones that will have like kind of commercially available silicon, especially for hobbyist developers.
No more questions? Okay then, going to lunch.
On the other hand, you're competing against George, the guy who's going to talk really fast and never shut up. So you might be a great teammate.
Well, annoyingly, I normally talk really fast, and I never have enough slides. So I'm always done amazingly fast.
You and Henning should find a way to be in the middle. Henning never finishes on time, and he's way too many slides.
I have not enough.
Right. So if you would just be in the middle, you both, you know, be perfect.
Well, like basically, if I wasn't sick, like the flight over, I was just destroyed because of lack of sleep. And I get sick here, so I lose 2 days.
Well, unfortunately, you only got to work for 1 hour. That's it. You get your hour of work in.
This is my wife, Darcy. I've told you about him the other day, my buddy. Brilliant developer.
Like the thread pilot's an easier one, but we have other like IO tiles that maybe something random misbehavior would never see. It had some bitch different issues with proprietary.
That's crazy. It's crazy. I don't want to. You love it.
Some of them lend themselves more to actually scripting through, and other ones you just for hospitals, not for profit.
Wow, Aaron's thinking about Haskell in my room. So yeah, I can.
Finding the core.
The only bop I'm going to is tomorrow with Metabug. You're not a good Metabug IRC person. If you're here and you don't go to Metabug.
Maybe I won't go then.
You'll come into IRC like all this shit being said about you.
I'm going to review my slides for a bit. Remember what I said.
No, we have it all at work. Yeah.
Like trying to pick his brain about.
I mean, in fact, it's trying to put up this PhD on the new laptop. Yeah, that's
Like I said, the warning is basically a lot of it's some of it's going to be generalizable, and probably a lot of it is going to be specific to us. So I don't know how useful all of it
no way. That is so right. Yeah, that's what we're doing. Ah, man.
Oh my.
Have a
Okay, thank you. Again, another one. I mean, you're on the internet right now, so you can talk.
I'm on the internet?
Yeah.
Oh. Hello, live stream. Hello, world.
That's Michael Lucas. Yeah.
What would you like me to say?
I don't know. What do you like you to say?
Ottawa's nice. You should be here at BSDCan. If you're not here, it's your loss.
I completely agree. We got some nice books.
Yes, I have books.
Cool.
Brand new one is the ZFS book.
Yeah.
You can get that at Amazon or whatever bookstore you like. Has this beautiful wraparound cover. And here's the specialty file systems, which also has beautiful artistic wraparound cover.
Nice.
You do not get the wraparound cover on the ebooks.
Nice, nice. Yeah. Good. Good stuff.
actually, like, I needed this, like, Mark Johnson is a, well, he's not inline, but he's hacked it, so he's fixed FBT tracing to work with tail call optimization. I'm just saying, he's got working on these things, right? Well, it's work. I shot some Mark about that. He's got some janky thing where he this is when the jump that is actually working tail call, and then patches it, but I think he's situated at the end of returning it actually jumps directly to the right thing. I shot some of the work done because I really would like to track it. So the thing, well, so he does this. That's how it does it. Yeah. Actually, Dwarf 2 does it. Yeah. He doesn't need any Dwarf. Mark seemed a little, because I had mentioned it earlier in the PhD thing a couple days ago. He seemed a little sketchy with the thing that he talked about generating CTF from 4.5. That's sketchy in those things. Yeah, it's sketchy in those things. I'd rather just use Dwarf. I mean, FreeBSD doesn't matter. I was talking to a Delphix guy actually. He was saying they don't really care either. I mean, Dwarf is bigger, but like they don't care. So Matt was kind of yeah. I mean, realistically, it's already shipped to yeah. There. Yeah. It's just kind of how are the problems with CTF? Yeah, it's a pain in the ass. I've just seen they have to think they at least one of the CTF performance or something. Yeah, okay, yeah, it's an addition, but Dwarf has just yeah, you can do more about obscure things. You do more of what GUS would do, which is nice. One way, right? I didn't realize it. So, but apparently, Saturday was not sure, claimed that optimization patents, it doesn't know we did it, like, but that's like, it's stupid, actually. Yeah, so that's why lots of times when it, like you said, optimization claim, tons of local variables and stuff all optimized out, and then if you go to the assembly of the registries, you get quicker now, than planning your registries and planning variable. Except it's good. And some of your GCC did a better job of that, so it's much better. That's also something that we raised to help young folks with the foundation. I don't know. I didn't know until talking to Vivek, that's why. So yeah, I heard people complain, well, things are affordably better. No, it's not. I mean, you can improve the compiler to do that sort of thing. So yeah, my friend is doing all the implementation here, live update, AS1, things like that. So it's losing a lot of too much information to be as it is just kind of happen all the end for certain information. It's not like a long-term solution. Yeah. But I mean, people are well raising it. People are using elegant, which is compilation, debugging, yeah, and instrumentation. Well, you don't have to
So it should be interesting, but I'll just.
You guys hear me?
Probably.
I can't hear you. That's a nice question. I think I'll give folks maybe one more minute. This is what happens when you have a talk after lunch. You know, I think people are gonna take their time. All right, I'm gonna go ahead and get started. Thanks for coming, everybody. My name is Mark Heily. It's my first time at a developer summit, so be gentle, please. I want to thank Chris for inviting me to come out and give a talk on JobD, which is a system I've been working on for about 9 months. So I'm going to give you a little introduction to that. Talk about a little bit of the history, where it's going, where it is now, and how it could be used to help FreeBSD, move forward in the realm of init systems and other things. So a little bit of history before I get into what the job framework is today. So initially, when the next BSD project was announced about 9 months ago, I was really interested in LaunchD. And I'm like, wow, it's about time that somebody is bringing that to FreeBSD, because I've been, I'm paid to work with Linux systems. I've seen systemd and Upstart and that whole debacle. So I've seen what happens when init systems go wrong. And LaunchD looked like a very clean, small implementation of an init system that offered features that the current RC system does not. So looked into the level of effort to get that working, and it turns out that you can get it working, but it's very painful. Basically, you have to bring over all of mock, and I'll get into some of the reasons why I decided LaunchD was not exactly what we needed in a later slide. So then about maybe a few months ago, I took a step back from the problem and started looking well, maybe the init system is not exactly the right conceptual model that we want to have for this. When you've seen the trend in, when you look at what systemd is doing, what you look at LaunchD did 10 years ago, is that you sort of abstract away the idea of a service in a traditional sense, where a service is just some daemon program that you run in the background. And you start to bring in other concepts like replacing cron or replacing inetd, or spinning up service on demand based on an IPC request. So clearly, I think the concept of a service doesn't fully cover what a modern system could provide, and we have examples of systems that are doing more than what services are. So I took a step back from LaunchD and said, like, what can we create a conceptual model that fits a little bit better towards the kinds of flexible systems that can cover not just traditional services, but things like cron jobs and other stuff. So what I came out with is the job framework. So when I talk about the job framework, I'm talking about a whole bunch of things. So like basically there's the whole concepts, which I'm going to go over at these slides. But there's the actual implementation of the configuration file format. You have a job manager daemon, which is kind of like the kernel in user space in that it schedules all the jobs, loads jobs, unloads jobs, manages jobs, all that kind of stuff. You have a set of command line tools to interact with that daemon. And I took it a step further and started thinking of like, we need a library basically that manages jobs, and that these command line tools would be built on top of, and not only command line tools, but IPC frameworks. So LaunchD is tied into Mach, which is not entirely portable, but there are things like dbus, there are other IPC frameworks, so I started thinking, well, like maybe we just want a generic IPC hook layer. So there's kind of a lot of stuff wrapped together, which is probably more than we want to talk about all at once. So I'm just going to call it job D from now on. I think it's like the easiest way to just refer to everything. So what is a job in this model? Job is basically 7 different things, any combination of them. So you have preconditions, things that happen before the job can run. You have dependencies that the job has, which are basically things that the job needs to be able to run successfully. You have the execution context, which is specifically changes that need to happen to the process to make it do what you want. You have the program, which is when you fork and exec a new program. It's like a set of arguments that get executed. Then you have some post conditions. So the program terminates, like what are you supposed to do? You're supposed to restart it. You're supposed to notify an administrator. You're supposed to just leave it, let it go. You're supposed to tear it down, get rid of all its dependencies. Like what do you want? It's just a set of conditions that take place on a lifecycle change. Jobs can also expose properties and methods. So somewhat of an object-oriented concept in that when you create a job, you can expose properties, which are basically just variables, to users to be able to manage that. And in addition to the variables, you can expose methods. Like, an example is like when you run Apache, you can do Apache service Apache status, and it'll print out a little status thing for you. So the job framework doesn't really care what these methods are, what the properties are. It just provides the mechanism for you to expose that to someone who would be using the job. So I'm going to go over all of these in a little bit more detail. So preconditions, like what are some of those kinds of things? So traditionally services just run when the system boots, but I think we can do a little bit better than that. We can do services that run at a certain time interval or certain calendar dates. You can do sort of like batch scheduling where you can say jobs that should run when the system is idle. And you also want to have socket activation jobs. So like the job D framework, or the job D daemon would listen to a certain port. Whenever somebody connects to that port, you want to say, all right, this is time to start the job. And you guys can feel free to stop me at any time if you have questions. So dependencies are something new. You don't really see that in LaunchD, not so much in system E either. But a dependency in the framework is anything that the job owns and that it needs to have in place before it can run. So in the example of Apache, like you need the Apache package to be installed. You need a configuration file for Apache that tells it what port number to run on, what its server name is, like a various number of things that it needs in the configuration file. you may want to run it in a jail. So in that sense, the jail becomes not really a first-class object, but the jail is more of a kind of utility that's wrapped around a program. And the job D framework takes care of building that jail and destroying it when the job is complete, if you desire it. You can certainly keep persistent jails around if you need to. Sorry about that. And along those same lines, you can bring up virtual interfaces, set up custom file systems, create mount points. So the mount point concept is really useful if you want to create kind of like, if you're not running on FreeBSD and you want to create a chroot jail, you can set up your chroot jail using job D so that it's there by the time the program is ready to run. All right, so the execution context, very specific things that take place. Job D will fork and then run various system calls to make the program do what you want. So it could be setting a user UID, GID, setting an alternate route, applying resource limits, redirecting standard output. Basically any transformation to that child process that turns it into what you want to have in place before the program runs. So then the program should be pretty simple, just an array of arguments, so you pass it to the exec call. And then post conditions just say what should happen when the job terminates. You can do automatic restarts, you can do notifications, brought in some concepts from Solaris SMF, so that lets you kind of mark a job as failed or faulted, so that you would need an administrator to correct the fault and then clear the fault. So, and also lastly, you can have transient jobs. So if you want to run a one-time job and you don't really want to keep a record of it around in the job table, you don't really care to keep any of its file systems or dependencies around, you can mark it as transient and then it just disappears whenever it's done, assuming that it completes successfully. So properties I alluded to earlier, but here's some specific examples. You know, again, using Apache as an example, you can set various variables. So the idea is that these properties would then be used to generate config files or to do variable substitution within this set of command flags here. So that if you wanted to pass in parameters, you could do it that way through parameters, through properties that the user can then manipulate. All right, so lastly, methods. Right now, they're just simple scripts that you could run. I could see this being developed further once there's an IBC framework in place, so that you could call IBC methods and that those would spit things out. It's very difficult to talk about IBC though unless you commit to a specific framework like dbus, which is certainly something we can look at, but I don't want to consider that in scope for the initial stuff. So what you end up with is something that's not just like an RC replacement. It's not trying to map one-to-one to what a service can do. But what I just described could be considered like a foundation class for a number of different types of jobs that run on a system, like a cron job, at job, something that runs out of inetd. You have your traditional services, even like the traditional jails. Like if a jail administrator wanted to create a jail, I could see like the jail command being rewritten to have some of the jail management stuff run on this rather than like rc.d type stuff. And the same with a virtual machine, since a virtual machine is just a process. It has a lot of commonalities with jails in that you need to have a virtual network adapter come up. You may need to have firewall rules associated with it. It's a process that starts up. The process gets arguments like memory size, disk size, all that kind of stuff. So the intent here is to have a framework that application designers and tool builders can use to kind of cut out that kind of repetitive task of like, all right, I want this thing to run at boot, and I want to pass these parameters to it. And I want the user to be able to start something, stop something, enable it, disable. Those kinds of functionalities can be pushed down to the job layer so that when you write a new tool, all you have to write is the stuff that's really specific to your problem domain. And I also just want to show kind of the tree of what dependencies could look like. Obviously not all of this is implemented now, but you know, I think it's kind of an interesting concept to be able to extend the notion of a dependency into new areas. So for example, users and groups, you could say, I want this program to run with a dedicated UID and GID. It's just, you know, in the past you would use nobody to run things, but that's just one shared account. But you know, in theory, you could say like, you know, automatically assign me a unique UID and GID for this job. When the job terminates, that UID, GID gets deleted and reclaimed. Same with like network interfaces. Firewall rules, I think, is another interesting one because manipulating the firewall outside of your normal service configuration, I think, is uncomfortable. And I don't see a reason why you couldn't combine rules that say like, all right, allow this network range to access this service that I'm running. Why couldn't that just be in one single config file? And why would you have to have somebody like set up the application over here, then go over to their firewall over there, put in the rules, and never the two shall meet? So I would like to automate that. Same thing with building jails and other stuff. That's traditionally been like a manual step outside of what you're actually trying to accomplish. So that's basically all I had about the concepts. Any questions before I move on? Yeah.
Dependencies, they're all just external dependencies to other things. Can you depend on other jobs, cascading, or something like the RC system where it says provides this and some other thing says, oh, I want that thing first?
Yeah, that's to be determined. Like really, so the origin of this system being in LaunchD, that was very frowned upon in LaunchD. So the idea is that you would never set up explicit dependencies and you would have socket activation take care of that for you.
So the IPC takes care of that. It says, now this thing can happen.
Yeah, exactly. So it's like this service needs this thing, so it tries to access it, and then the job manager or LaunchD or whatever would say, okay, somebody needs this, I'm going to do this first. So that's one approach to have it. I'm not opposed to adding explicit dependencies. I think that complicates things, and it's really kind of an open question. I think probably you would want to decide that before you got serious about replacing RC. Like, do we want to keep the manual explicit dependency kind of thing, or do we want to go to like socket activated or IPC activated, bus activated, those types of things? I think it would be an interesting argument to have. I'm not sure I'm fully on one side of the fence or the other. But, okay. Yes.
So even without that, can dependencies depend on other dependencies? So you have to have a jail in order to install packages into it that are needed for the service?
Yeah, so if that's done through jobd and through the configuration file, that the ordering of those dependencies is implied by jobd itself. So jobd knows that like before I can start this program, I have to go and make sure all these dependencies are satisfied. Like I have to make sure this jail exists, I have to make sure this interface is up, and it has this IP address, and like it has these firewall rules tied to it, and you know it has these packages and blah blah blah. So yeah, it knows the order of operations to achieve all that stuff through some internal knowledge of how you would have to construct something like that from scratch.
Oh, so it knows that it has to create a jail before it installs packages, for example?
Exactly, yeah.
Oh,
yeah.
okay.
And I can show an example of what that would look like in a config file later. Yes?
Yeah, particularly interested in Chrome replacement. What are you looking for the time resolution on your service, basically? How frequently I can schedule job?
So there's two different schedules right now. There's the simple interval scheduler, which can work per second. So you have a 1 second interval. The cron part is halfway fleshed out, but I've been looking at using the boost library potentially. They already have some cron-like functionalities. So I can't tell you exactly what it will be, but is there, what are you looking for in terms of?
Yeah, we're basically looking at at least second resolution, 1 second resolution. But I mean, in this in 2016, I think you should go further than that because 1 second is pretty long time these days for a lot of things. And another thing that I particularly don't like in cron is that you cannot schedule something to run at specific frequency. So you don't necessarily, let's say I have a job that I want to run every 30 seconds, but I don't really care if it's running on 1st second and then 31st, or if it's running at, I don't know, 5 seconds and 35. I just want it to run every 30 seconds. That's all I want. And with cron, it makes it difficult because if you have several such jobs, they all start at the same time unless you know, manually tweak it to run at 1st second, 2nd second, and so on. So it makes it a little bit difficult to spread the load across the interval.
Yeah, that's interesting. I think it's probably not something that Jobby can help with immediately, but you know, I'm open to. So since we're not like restricted to the classic cron interface, like feel free to suggest you know, lower time resolution if that's what you mean. Yes.
The other thing that's interesting is adding some jitter to adding explicit jitter to the cron, so that if you set a job to say update all your packages at midnight on every day, you're not slamming your server with 10,000 machines all trying to update the packages at the same time.
Yeah, and so that gets into another part I didn't mention is there is no distributed controller for multiple servers at this point, but I think that would be a very interesting project for somebody to tackle, because when you start getting into managing thousands of servers or virtual machines or jails or whatever, I think it would be important to have something that's aware of like overall scheduling. So there are already a lot of frameworks out there like Mesos and stuff like that. For the Linux world, I'm not aware of you know, general purpose stuff for FreeBSD. Yeah.
So like the way we do that, like in Jenkins, I love its interface for this, but you just say like run it at H, which is hourly. I don't really care if it's 0 to 60. Pick a random time and run it, or you know, minute times 3, or you know, whatever it is, and then your job system would just pick a random integer, and that kind of avoids that issue where you have all these systems that need to do something hourly, but they're all picking random times.
It does, but it does not fully, because in this particular case that he mentioned, I think they want to run it about the midnight or whatever when the load is low on the system, but they don't want to have it specifically at midnight also. Sure. Because they want to have some spread, but not full.
You almost need ranges in that case, like pick a random between these.
Yeah.
Yeah, it doesn't really matter exactly how in this case.
Well, I mean, I'm thinking about my own applications, and we definitely, if we run, for example, backup on the system, we want it to run in the off-peak, obviously, but specifically there is some range of times that we
I mean, when we're global, we don't really have off-peak. The other thing is that it feels like trying to cater to all the use cases in Jobby just is too complicated.
Yeah, so I do want to offer a plugin API so that the core doesn't have to necessarily solve every single use case, but that you can have certain hooks that like this job, because you know we use a JSON configuration file, so that the plugin could be given access to that file, be able to you know hook into certain parts of the job lifecycle, like when it starts, when it stops, you know, things that could run in the background and raise events. So I think there's some room for some interesting things that could be added onto it later, but you know, first I'm trying to set up the foundation, of course. Okay, so if there's other questions, I want to go on to some of the tie-ins between Jobby and FreeBSD so far, because I've been using FreeBSD as my main desktop for about 9 months, and so like most of my tinkering has been on FreeBSD, and that means FreeBSD features have been you know, implemented in preference to other operating systems like Linux. But it's interesting what I heard from the goals meeting yesterday for FreeBSD 12 goals. You know, you want to replace the RC.D mechanism. You want this new replacement to use machine-readable tooling, so something like UCL, where you can parse it, emit it, edit it with the machine, not require human editing. Supporting IPC between the tools. You know, libnv I think was mentioned as an IPC mechanism. And also that tooling should be built around libraries, that other tools can also use those libraries so that you don't have one CLI tool talking to another CLI tool and being bound to its user interface. So those are already goals that I had in mind for job D, so I think there is some good progress in that direction. But I just put together a chart showing like where we are now with the RC system. Probably the number one competitor that I would see to job D and how job D handles that. So RC, obviously shell scripts are not machine readable other than the shell itself. You can't do something like a JSON parse and edit and re-emit the shell script. So I'm going to talk about Nosh in a minute. I think that is the most complete alternative to job D. But it's still based on shell script, so it's a custom domain-specific language using the Nosh shell script. Not really standardized in a way that tools can easily edit it. But job D uses JSON throughout, so anything that speaks JSON can edit job files, create new jobs, and work with the IPC system we have. So from IPC, RC, obviously no IPC to speak of. Nosh really doesn't have IPC that I can find, but today job D uses JSON RPC for internal communication between its tools. What I'm interested in doing is opening up that to create kind of like a job RPC so that jobs could talk to each other. One job could call a method on another job and so forth. And this is also interesting in the context of Capsicum, where you want to be able to pass a file descriptor to a process that may have certain rights, or you're running in a process that has no rights and you want to pass a file descriptor you own to something else to dump data into it. So I think there is a use case for a machine local IPC system that I don't really think dbus was designed with that in mind. So my initial thoughts are to wrap JSON RPC inside of libnv, so that libnv can handle the file descriptor passing part of it. It can provide the variable that includes like the JSON RPC payload. You can do like API versioning. Just a very simple like libnv transaction that can give you what the JSON RPC spec does not for this application. And then lastly, the library aspects, like RC is not, well, I mean, you do actually have RC.subr, but I don't think that's the kind of library that people want. They don't want a shell library. They want C interfaces that they can call from their program to like query a job, create a job, modify an existing job, start a job, stuff like that is not really possible with RC. Nosh doesn't have a library interface that I could find, but job D has a initial implementation of C++ library. I do plan to support both C and C++ to different degrees. So I'll just go over a little bit more of the platform exclusives that I've implemented on FreeBSD already. So I've already done some work on Capsicum. So my idea was we would want to be able to create a sandbox outside of the program source code itself using job D and say like, this job runs inside of this Capsicum sandbox. It has these file descriptors that have these rights. So that is implemented, ran into some problems testing it. Basically, that's a limitation of Capsicum not being able to run. Yes?
Yeah, actually, we fixed that.
Oh yeah?
So you can now pass a set of directory file descriptors to the runtime linker instead of a set of directory path names. And so you can use that to look up libraries even from capability mode.
Yeah, I tried doing that, and then it still had the same issue. So what I think it was that it couldn't open the linker itself. So because it's a little different use case. I think Capsicum has all along been designed that like you're modifying the program's source code. You've already done your dynamic linking, and now you're trying to execute something else. But you already know where the linker is, and it's already loaded into your program. I think it's a solvable problem, but it's why it's not fully working today. Is what I'm saying. So ZFS dataset creation, jail. So the hackathon really went off on a branch, did some pretty interesting work on jails, dataset creations, network interface stuff, poking holes through from the main system to jails. Lots of interesting stuff that you can do with this branch, but it's very experimental, not production quality at all. So I'm using it kind of like as a guide for when I have time to actually come and bring it back to the main line. But it is pretty interesting and cool to be able to like spin up a jail like instantaneously using, having its own dedicated ZFS data set, having its own private IP address with port pass-throughs created, and that is cool. So I think that is coming. As well as the image interface creation. It's not something that I have started doing yet, but I've looked at it, and it's probably on the near-term roadmap. So let me just talk about the other alternative, like LaunchD. I know has been talked about a lot. I really think it's a dead end, though, in several ways. I mean, number one, like the upstream has gone closed source. They deleted the project from macOS Forge. It's been several years since there was a total rewrite of LaunchD that has been tied to like their XPC IPC framework. That is closed source. I don't believe it's going to be open sourced. I mean, I have no magic ball to tell me what's in the mind of Apple, but from my perspective, the open source project's dead, so it's going to be difficult to resurrect it. The other reason is it requires mock, so it's really taking on a significant tech debt for FreeBSD to import all of mock, and or the amount of mock that you would need to make LaunchD work unmodified, I think is a very unpleasant thing to contemplate, as well as it really ties you into only working on FreeBSD, and like no other OS that I know of is chomping at the bit to implement mock at this time. And there's also just a number of issues and kind of deficiencies of LaunchD. I think the way that it was designed as a consumer OS product, it was never designed to be used by a power user or a Unix system administrator. So the interfaces and the command line tooling leaves a lot of things to be desired. For example, like with the RC system, you can have flags and pass flags into your daemons. So you put something in rc.conf to influence how your job runs. That's not a concept in LaunchD. So you would have to like unload the job, edit. I mean, you'd basically be building like a giant hack around what's already there to make it do a simple thing like pass a flag into your program. It also doesn't have any of the kind of enterprise fault management, state control stuff that I liked about Solaris SMF. I was a Solaris admin for several years, so there's things I don't like about SMF, like XML and kind of how over-engineered it is. But I think it has some solid ideas that if you're running a server, you want to be able to say, like, show me all the servers that are actually faulted. And I want that to be in like bright red letters. And when a configuration file changes, like, I want to know that this service has not been restarted. So there's these kinds of state management functions that LaunchD just doesn't have. So in my opinion, it's just not very sysadmin friendly. So even if you put in the effort to get mock, put in, committed to using dead code from an upstream vendor that's abandoned and it's not supporting it, like you're still not getting a very great product at the end of the day. Like there's some cool ideas in LaunchD, and I still like that aspect of it. So that's why I started implementing it independently of the original code base. So Nosh is another funny one. I think it's been around for several years. It reminds me of Qmail and some of the really classic Unix, everything is a file and pipe, run everything through a series of pipes to get what you want kind of thing. I think it's an interesting experiment, and certainly don't want to take away from the hard work that's gone into it, but it just doesn't seem like it fits with what FreeBSD wants, especially like some of the aspects that came out of the goals meeting yesterday. Like its configuration language is totally custom. It's not machine editable by anything. Doesn't use a library, doesn't have IPC. So while it does give you some of the things like socket activation, I just feel like personally they're implemented in a very strange way. And I want to write software that's useful, easy to understand, easy to use, and that everybody can participate in and make better. But I think the way that Nosh is run is more of like someone's personal pet project to kind of experiment and research on their own, which is certainly fine. But the fact that it's not in source control, it doesn't have a mailing list, there's no chat, and the author specifically says he doesn't use email, which is a lie, but I've seen him email a few people. But it's sort of like, I wouldn't trust that to be my enterprise grade RC replacement. So there's also advantages to Job D. Obviously I'm biased as the creator, but it has been ported, it has built on 5 different operating systems, works on Mac, Linux, most of the BSDs. So you're already getting something that's out of the box, where people from different OSs are able to participate, use it. I see it as potentially a replacement for systemd in Linux distributions that don't want to buy into 100% of what systemd is selling. Systemd itself is a very large project, and so if you drink the Kool-Aid, it will give you everything. The other day I heard it came out, they implemented their own DNS resolver. So instead of Unbound, you would just use systemd binding, and there's all kinds of uproar about why are you doing things this way. It's I don't particularly care for that style of development. Replace everything, kitchen sink kind of, here it is, take it or leave it approach. But Job D also has a very low barrier to entry in that it works with the existing init system. It works with PID1 still being init in the same way it is today. I think in the distant future, if people ever decided that there was some massive benefit to putting in a PID1, go for it. But I'd rather start at the other end of the problem, convert things over slowly to use the new mechanism, run them both in parallel, try it for a few years. Once you're really comfortable with it, then you can start dropping old stuff and revisit the whole architecture at that point. But there's already been some work with creating the proc-ctl syscall so that running as PID1 is not as important as it used to be. So I think really there's no reason to put your system at risk, break your init process, break the ability to boot your system, or not have a functional single user mode or terminal. I don't want to cause any damage or deal with all the hard problems up front. So trying to solve the easy stuff first and then leave the hard stuff for later. And Job D is really intended to be a reusable framework. So it's not just an RC replacement. It's something that could be used to build other new tools that we haven't even thought of yet. New container managers, VM managers, distributed job managers, it's just sort of there to be a utility that you can extend to new use cases. And lastly, it's really trying to be user-focused. I'm a sysadmin, I use Puppet, I use various things because I have to, but I don't necessarily like it. So if, I'm in a sense building an application that could make my life easier, when I want to install Jenkins, or I want to install a new Apache web app, and it requires Ruby and these libraries and Apache and firewall rules, and needs its own user account and blah, blah, blah. So you basically have to use Puppet to keep your sanity. And to me that just points out a missing part of the operating system where the operating system has all these things. It knows about users, it knows about packages, just they've never been tied together at the OS level before, so that you always have to either bring in a third-party package to manage them, or do it all yourself by manually going to one thing, setting that up, going to another thing, setting that up. And so I just want to reduce the amount of fiddling and effort to go from 0 to a functioning application. So I have an example of kind of what I'm talking about, with the current jail RC stuff, you have a large number of variables in rc.conf that you can put in. It's, to me, a very unpleasant combination of jail underscore jail name underscore some other variable name, and even this whole idea of writing essentially a script by adding a number to the end of it is it burns me to look at that kind of stuff.
To be fair, that's not jail management anymore.
Right, I understand. I'm not trying to cast too much shade on this, but it's the kind of thing that you have to do when you don't have arrays, when you don't have a complicated, when you don't have JSON. You can't say here's my jail key, here's my example key, here's all the properties, and this is just not very, this is the kind of thing that I'm trying to avoid, not this specifically, but I would rather have jail management look more like this. So you say here's the name of the jail, here's the program I want to run inside of it, give it the host name, give it the address on this network interface. So in a sense, the network interface, the jail is kind of separate. You could have the jail like JobD knows that, oh, I'm building a network interface and I'm building a jail, so I better like plug the two together. But you're not explicitly saying like create this and then like, you know, apply it to that jail. So, yeah.
So, for example, in that thing, if you took the jail part out, the whole thing would run just the same way, but just not in jail.
Just not in jail.
Okay,
yeah.
great.
Mm-hmm. So this is kind of a diagram of how I was showing, like, you know, your complex application deployment. So you had a FAMP stack of you know, FreeBSD, Apache, Postgres, some config files. You wanted like a log rotate cron job, and you wanted it to run into jail. You wanted to use PF to secure it. Basically, you're asking the user to go to all these different things, set them all up in a specific order, and you know, then go and have a beer. But I would rather have it where you put all that kind of complexity into a single JSON document that describes all the stuff that you want to have happen. Feed that into JobD. It does the magic behind the scenes for you, and then the user can just start using the new application with the default install and maybe start tweaking config settings and stuff like that. So you don't have to like deal directly with each of those layers underneath. So a more expanded version of that magic would show that, so JobD would be creating a dedicated data set for that jail, creating a dedicated interface, spinning up the jail, launching Apache Postgres, generating the config files based on like the properties of the job, setting up the cron job for like your log rotate or whatever, as well as like applying the firewall rules to let people start using that application. So that's kind of like the bigger picture, like at the end of once all this is implemented, that's what I want to have happen. Yes?
Just a quick question, does it handle automatic updates? Let's say I'm changing my web app, JSON, whatever. Does it handle the reconfiguration of the thing?
So that's an interesting question, because this has not been built yet. Like, this is where it's going. So right now it doesn't handle that. I think that's not something I've really put a lot of thought into, but I don't see why not. Like, you could give another, you would probably have to download like the new version. So instead of just my web app, you'd be like my web app version 1. If you would apply version 2, like there would have to be some kind of upgraded path in there. So that's an interesting question. Like I can't tell you.
Let's say I make some mistakes in firewall rules and I want to change this from the Z file. So how do I do that with the
So the firewall rules would be based on the properties here.
Just for example.
Yeah, sure. So you'd have like firewall, like imagine instead of, like underneath the jail it said like firewall rules. You say like allow from, and then there was an array of different IP blocks that you wanted to allow. So you make a mistake and you reconfigure that, you could then reload this and it would do basically a diff and say like, all right, here's the list of rules that are actually out there. I'm going to look at, here's the lists that are defined. I'm going to create new ones and like get rid of ones that are not there. Any other questions?
Sure. Yeah. So the picture that you had of the simplification of, the previous one, well, picture.
Okay.
That sounds in some ways like tools like Docker.
Yes, I'm glad you mentioned that. Yeah, I think it does play in the same space. It kind of brings Docker back to more of a native OS facility. Like Docker is like a layer on top of something, so you're running in a totally separate container. My vision with this, especially with jails, is that you're punching holes from the host into the jail. So this could be a Docker alternative. It could be, I think Docker has some interesting use cases for continuous deployment, building stuff on other people's Docker images. So I'm not going to say like this is not going to replace that. But I think if FreeBSD or any other OS shipped with more usable kind of these my web app JSON by default, so that like you could go to the app cafe or the program store or whatever and be like, oh, I want to run this Ruby on Rails web app or this like Django thing. And you're just like clicking on that and it will set it up for you. I think there's some value in that above and beyond just going to like a random Docker hub. User space and getting stuff. It's like it offers the ability to tie it much more closer to what.
So my question was actually kind of the other way around. I was in no way trying to imply that Docker is the right answer to
okay, good,
problem.
yeah.
I was more thinking, would it be possible for you to host Docker images using jobd? How much framework would you have to put on top if you say, well, I've already built something that can create you a jail and run an application in it, do a bunch of configuration? Could we run Docker things with jobd?
I don't see why not. Like, I must admit I'm not too familiar with the internals of Docker, but I couldn't see why you wouldn't have like, you know, a Docker section here that says like Docker, you know, image, and go grab this image from Docker, and this is what I want to run as my program. Maybe you wouldn't even have a program at that point. Like, if you're referencing Docker, like it already has its own like Docker start command or something.
You probably just need a kind of transformation from the Docker file to the digital file, and it should be enough.
Yeah, so that's, I'm kind of wondering if, are there things that Docker does that you can't express very well with jobd, or could you in fact write a tool to say, take this Docker file, just transform it into a jobd conf file and Bob's your own code?
What's interesting about Docker is not the Docker file of the way it runs on your box, even if that's what people see, is all the ecosystem around it and how they cache images and how they do provide through proxies and cache stuff. And so this, in my opinion, this can only replace the Docker command line in the box, but you need something else to replace those parts.
Yeah, it's an interesting question. So, I mean, I find this an interesting project to hack on. I'm certainly open to other people bringing, you know, their engines to scratch and, you know, start answering some of these questions, like, would it work in combination with Docker? I don't know. That's a good question. Any other questions? All right, we'll take them over time. All right, thanks, guys. Appreciate your time.
Oh, I have a question.
Okay.
What's job you've written in right now?
It is C and C++. So originally launched it was in pure C. When I started bringing in these larger concepts, thinking about IPC and all that stuff, I realized that C wasn't going to cut it, and the lines of code you'd have to write and the amount of risk you would have to incur would be great. So it's basically like a very thin C++ wrapper around a C program right now, with the idea that it's going to evolve and be more C++ native over time as things get converted over.
So since nobody's actively trying to get you off the stage.
I don't think there's anybody scheduled after me, so I'm happy to keep going.
Okay. You had talked about post conditions for the job.
Yep.
So when the job exits, terminates, whatever you want to say, you can set up things to happen at that point. How do you determine that the job was completed?
So when the process exits, jobd is notified. It is monitoring the process. So it will read the process status and will exit 0. We assume that is the good exit condition. Did it die non-zero? Did it catch a signal? Something like that. So it considers 0 like success, anything else is failure. And then it lets you layer on things like, do you want to keep alive and automatically restart it? Do you want to send a notification? Do you know, otherwise it will show up. If it fails, it will show up as a faulted job.
Are you assuming that the process you fork off is the process of the job? And, you know, I'm thinking about typical daemons that are written, they will call daemon. And so now you don't have the original process.
So that's a problem, yeah. Look, the Upstart developers solve that by letting you say like how many times the daemon forks, and you can track it that way. I don't really like that, but I think from a practical standpoint, nobody is going to rewrite every daemon out there to not do that. But I think you know, one of the good things about systemd is that systemd also operates that way. So I think over time, most of the popular daemons will allow you to run in the foreground. And so if there are daemons, I mean, there are plenty today where you can pass a flag so that it doesn't demonize itself. So you definitely, as you're converting it over to run on your job, you have to make sure that it doesn't fork. And the code to actually follow it across forks is not really written yet. But you know, I can see if you have jails, you may also be able to say things like if there are 0 processes left in the jail, we'll just assume that means that the program has died, so that you can kind of infer whether or not it's successful. You know, I think it's best to handle it in the source of the daemon. If you have to patch it to get it to do the right thing, I think that's a better way to go. But realistically, there may be these other kinds of mechanisms that go with that. Yeah.
One particular automation to end up at on S.M.A.R.T, you have the contracts where you can do the equivalent now on FreeBSD with the Reaper. And what they do in that case is if the program is double forking for whatever reason, then they fork the SMF itself, or job D in that case itself, it becomes a Reaper of the children, and then you can count, and we have added a syscall to the Reaper, and you can count how many children you have. So as long as you have children, you still run that. Okay. And there's a very good example of how to use that. It's actually a bit different in the BSDC from Dragonfly, which was written by Bukin when we designed the Reaper.
Yeah, I'm actually really interested in trying that. I'm glad I think you're right. It will make it easier to track like these double forks and kind of do the right thing without having to guess at what's going on. Yeah.
So in my mind, possibly a killer feature with this, if you looked at expanding the JSON schema to have a notion of resource control, like with RCTL. Like you only get this much CPU, this many disk IOPS, because that would play great with jails, or even launching a process and saying you're only allowed to, you know, spin this much.
Yeah, yeah. So LaunchD, it's basically inherited the set our limit stuff that LaunchD offers. But I'm totally on board with like going beyond those kind of standard limits and adding whatever platform specific things.
You have to use the other utility right now to go
after the fact. Exactly. No, I definitely want to be able to route those kinds of limits, and that's really what job D is like. Is to like apply these limits and controls and security functions and like transform the process into what you as the system administrator want to have happen. That maybe the original program designer couldn't like choose for you.
It's kind of interesting because I wrote something very similar to this for my company's product. Doesn't quite go to the extent that you have a vision you go, but in terms of basically starting out processes and monitoring if they're still running and establishing.
Yeah, I mean, I think a lot of this is solved problems. It's just all been solved in various silos. So like, oh, we want resource limits. Well, then you go over here and do resource limit. But we're never going to like wrap it together in some like, you know, single config file, single framework or management team. And it's always like, you know, these separate things developed at separate times with different people.
Are you going to say on JSON, or are you going to do on UCL, which will be something 100% compatible?
So I used UCL for a time. The reason I went back to JSON is that there's this really great C++ 11 JSON library that makes working with JSON the same as working with it, like a Perl, Python, Ruby object, like nested data structures without a lot of explicit iterations and all that stuff. So it was very useful to have that functionality. My plan though is to add support for UCL back in as an alternative so that you can define your job in JSON or you can define it in UCL, and then what I will do is have UCL do the parsing and then emit a JSON object in memory, and then my JSON, like my native C++ 11 JSON guy deals with the JSON side of it. UCL lets the end user write things in a little more user-friendly way than the JSON allows. I do have some reservations about UCL in that, like, I think there's also some benefit in having native JSON support when it comes to like other programs and other tools that need to be able to edit things. Like JSON is a format that's supported by a ton of stuff already.
Yeah, I mean,
and so I think like it's too early to like fully commit. Like UCL is not available on a lot of platforms. It's like, so I don't want to be locked into UCL as a hard requirement.
Yeah, sure. Well, just having support for UCL is useful because you have a lot of macros, sugar, you can add includes, you can have an override mechanism, so you just have your default progression there, and then something that can override in other places, and you have nothing to get that.
Yeah, it's definitely very cool. Definitely nice, but you know, when I did the C++ rewrite, I wanted to choose like what was the best tool for the job, internal communication.
Yeah. And well, so it's a very related question. It seems like the thing that you mostly care about is having some structured data representation. But if I want to dynamically create jobs on the fly, for example, really what I want to pass you is some data structure and not have to turn it into JSON that you then have to parse again, right? Will there be kind of RPC mechanisms in that way so that I can say, here's my sandboxed process, and now I want to spawn 20 worker processes with these varying parameters, so I'm just going to generate the stuff on the fly.
Yeah, so that's kind of what I want to offer through the library interface. It's not there right now. But I think it's going to be an interesting challenge, like because of the flexibility of the data structures, like you can leave certain things out, add certain things in. It would be a rather large data structure, I think, to offer, especially at the C level. libNV might be able to help, like if we wanted to make it a dynamic structure that you would build, but at the same time, like, yeah, I hear what you're saying, like it'd be great if there was just one symbol like job struct, and like I say, like, put this program variable in, put this UID variable in. And I think there may be a use case for like a simple job, and then like if you need extended job attributes, you may have to pass those into the JSON argument.
Well, I was in fact thinking of libNV in particular, just because if it allowed you to dynamically create a job or a description of whatever complexity, and then handle the arguments, or you don't, or you send an error to say I didn't understand this or whatever protocol you want to use, but that is a mechanism that you can take UCL and turn it into libNV or JSON and turn it into an NV structure. So you could potentially have something which, if you're building, and especially if you start to have more complicated sandboxed applications where you're building something here, you can build in an NV message and pass it to this process, which is going to add some more details. Pass it to this process, who's actually going to pass it to job data for the request to happen as we start to get more complicated sandboxing things.
Okay. So you're saying there's already support for transforming JSON into a data structure?
No, but UCL is not yet. It will be at the end of summer of code. And so there's some code right now where they are extending libNV, and they plan to add an emitter for UCL. So you can translate any libNV to UCL at the limitation of binary, no, not binary, because base64, at the limitation of file descriptors, of course.
But in the other direction, you can take JSON today, pass it into libUCL, and turn it into an NV object, right?
Or message pack, because natively UCL can export to message pack and parse from message pack.
Yeah. Yeah, that all sounds really good. So I'm definitely excited to see this come online. I do want to ask that these be split out into like standalone libraries or make it possible to distribute. Right now, I just kind of bundle a private copy of libUCL, and I think I have a copy of libNV in a branch somewhere. But it's really, preferred way, especially if we start talking about like Linux distributions or other places wanting to get, places outside of FreeBSD, like NVMe, may not have the same things in tree, like being able to build those dependencies as standalone libraries and things.
Well, that's why I bundled these libraries as well in package, because packages use out Linux, Mac, and so I put those libraries. Do you have plans? Sorry, I have missed it.
Yeah, it's okay.
Do you have plans to make with like one of those when they build I don't know how familiar with robots, but when they build S.M.A.R.T, they managed to keep all the usual tools of what the user sees, but they're also looking to S.M.A.R.T by itself. Meaning, like, for example, IDP becomes the regular service for S.M.A.R.T, but you have the console where people see.
So that is my intent, is that we can build, like I would like to see the service tool be rewritten so that it can
Or maybe if I'm running the slideshow, I might send you that.
Looking for the schedule.
It works on full screen. That's perfect. Yeah, I got Mike on as well. Yes. Okay. Yeah. Yeah. Good stuff. Yeah. It's just got forward and back buttons for your also just one of those. I should run this before my but it's not good.
Yeah, I had to miss the last hour of talks.
You can throw this in here because I talk. I do that except
I use this next door.
Okay. Talk for a couple of weeks. I'll say something about it. Okay, so press record. I gotta go.
Can you hear me?
I can hear you. Back row, you guys okay? Can you hear me? No feedback? It doesn't sound that good. Yeah, there's a little bit there, but not a lot. But it's it's concerning because those two speakers are both going over your head. We were talking like this.
Should we start? Yeah, okay, today we're going to present to you guys a combination of FreeBSD, BeagleBone Black and Robotics. First of all, I want to say thank you to everyone for being here. I know you have many talks over there, and you chose to see this specifically one. So my name is Edicarla. This is Vinícius. We are a team from Brazil, and we are very, very happy to represent our country today. So this is just a presentation overview, so you're going to see the topics we're going to cover today. First is the project and the prototype itself. Then we could bring the prototype here so you can see like in real life. For the device tree, FTT, there was some feature that we really use in our project, we know we're going to use in the future as well. And like what we expect from this project, what is next. If I'm talking too fast, please let me know, because I'm a little bit nervous, so, okay? So the project itself, when I say I build robots, so people say, oh, so what the robot does? They say, basically walks. It's basically what I expect with the Lego robots to do. But we went to a huge path to achieve what we have today. It's not just like a robot. So we have a robot that can be remotely controlled. Okay, cool, yeah. So one more than this. So it's a robot we can control through Wi-Fi, so it's totally wireless. So you can send to different environments, you can use for inspection, you have different use as well as academic field. The robot is the second version. In Brazil, BSDCan, so I don't know if you guys know about Vinícius, created the BSDCan in Brazil last year, and I'm happy to say that I was there and I presented the robot, the Bukin 1, first robot.
Actually, it was the second one, but it was the first one with the international speakers and public, so it was the biggest one.
Okay, so everything started when I met Vinícius, personally. Now I have FreeBSD, I'm very happy, and it was totally out of my comfort zone. I didn't know how to change directories, so it was really, I had to put a lot of effort there, and I'm very happy because now I use a machine that I know. So it was, and for Vinícius it was different because he didn't know anything about robotics. Like he's computer engineer, mechatronics engineer, so we kind of use our both knowledge to create what we have today. So if you ask me,
I think your thesis was about the robot, and I just told a joke about using FreeBSD. It was totally for fun, and we accidentally jumped into this.
yeah. But it's like we've been to 2 conferences, so I think it's doing a good job.
Yeah, it's really total out of the comfort zone of our entire laboratory. The research lab that we work in Brazil, people just get a BeagleBone or a Raspberry Pi and use the default Debian, and this works. They don't crash anything, they don't try to build anything, they don't try to patch or something like this, do a custom kernel image. And with FreeBSD here, it was quite a fun. We need to build a kernel image, we need to build the packages, because when we started the project, there was no official repository for ARMv6 packages. And I think that was Sean Bruno, Bapti, and these guys on IRC. I was there asking silly questions every time, every day, maybe. And they helped a lot. Touch with a server I could use to build these packages. I also reported back to the FreeBSD team. I opened up a PR in Bugzilla and said, hey, this package, you can work, it works in ARMv6, like paths, like libcrypts, and stuff like that. During this development of our bots, we also try to introduce the favor we're getting from the software producers.
Okay, so I'm proud to say that it's the only exapod robot that runs FreeBSD. For now, you know, maybe we kind of give it to someone else, use the same thing. So, like, using these different and unique features, you know, this innovative concept, we decided to build one, and that's what we have. We wanted to say thank you for the lab. They bought the lab that we work in Brazil, so Laboratório de Inovação Tecnológica, they give us support, financially mostly, and they play, so basically is this. Well, so what exactly this talk guys by now look at you. The difference between these two is the one it wasn't wireless because we still had the DC power supply connected to it. And here we have the batteries. We have also different features, but hardware, if you think about hardware, this is the major difference between these two. And this one wasn't walking, and this one walks. I think it makes it a whole difference as well. Because I said that the robot walks. Imagine I build a robot that doesn't walk. It's a shame. So I'll describe a little bit of this system. It's a bio-inspired robot. Do you guys know what is a bio-inspired? Or you probably have a clue. Okay, it's inspired in a live creature, insects. This case, it's not a spider. The spider has 8 legs, and this one has only 6 legs. So it tries to reproduce the way the insects walk and the whole body structure. That's why it's called bio-inspired. In this robot, we make use of single boards. So each board has its own function. And we put all of them together, and then we can make the robot walk, receive commands, which directions should it take. It's a ROR. I'm not sure if this is the correct classification, but I created it because it's my presentation. So I call it remote operated robot. It's powered with FreeBSD 11. One thing, I don't know if you mentioned, Vinícius, but when we started working with FreeBSD 11, it was a still current version, so they're still updating things. We crashed a few times, but we could learn a lot, you know, so yeah, kind of cool. And we do have a little bit of Python. Yeah, we can mix, not a little bit, a mix is the whole software. It's in Python and C. We also have a cyber client application via Wi-Fi. And with this we can control the 12 server motors via serial communication. So that's why we have 12 degrees of freedom. So this means basically that the robot can move forward and back and turn left and right, but it can't go up and down. Why we decided to, the hardware platform. So we had to do we had to choose. If you see insects, they have three articulations, so they can go up and down, do 3D, can move in 3D space. But why this robot doesn't do this? Because we were concerned about power consumption, weight. We wanted to be compact, so it was our choice to have only 12 servo motors. So, as I said, the robot makes use of single boards, and this is the hardware platform. So BeagleBone Black is the brain of the system. It's a computer, it's robust, and we can attach different boards to it. You have many I/Os. It's very compact. When you use embedded systems, that's all you want. You want to create something small. You don't want something big with a higher consumption of battery. So we have the BeagleBone Black servo motors, they're articulations of the robot, that's what makes the robot move. We have the batteries and voltage regulators boards. They together they make the power supply. They are power supply of the robot. Okay, BeagleBone Black. I don't know. Do you guys know BeagleBone Black? Most of you guys, yes. Yeah, great. So why? So I will talk about this. So basically, I will say why we chose BeagleBone Black. Well, first of all, that's one of the boards that we had in our lab, so we didn't have to buy it. Not the main reason, but one of the good reasons. Besides that, you see lots of documentation in internet, so it made our work easier. And we had an image from FreeBSD for the board.
Actually, most of our friends and co-workers in the lab are making fun of the bot because they work with PIC microcontrollers and Z80 or something like this, the other ones, and they wanted us to use these things, but how hard, I mean impossible maybe, would it be to use IPv6 and control it with SSH or I don't know that. There's an operating system here. We want to do that and to use a PIC controller or something like this.
Arduino, we can.
Arduino.
Yeah, last time, I'm sorry to interrupt you, it just came to my mind. Last time that I presented, so a guy asked me, so why are you using like a computer to do only this, like move some servos, receive some messages? And then I said, well, I could use Arduino, but then I think bunch of people already done this, and I wanted to use FreeBSD, so how could I put FreeBSD in Arduino? That was my main reason. And another thing, I want to use something like big, I want to be out of my comfort zone, I need to learn, I'm finishing university, I need to at least know a different operational system besides Windows, you know? So that was a perfect choice for us. It's very easy to use, like I said, all these other features that the board provides. So embedded system, compact size, lightweight, and low power and consumption, and the revision C. Okay. So this is a Chinese board, and it's what we use for PWM driver. Are you guys familiar with this PWM? Pulse width modulation. So that's what I use. It's a kind of signal that we have to use to move the servo. So I wanted to put in a specific position so the robot can move. So I need to apply this. The main thing is BeagleBone Black has only 4 channels, and I've seen people having troubles using 4 channels at the same time. So I decided to, why not use a board so I can dedicate the board just to reproduce PWMs, and then I can use all the features in BeagleBone Black. So I have more I/O, so that's why we decided to use this board. It's simple to use. You communicate through serial, like a word. And so I just communicate them to. I have a protocol, and I send positions to each one of the servers. It has up to 32 outputs, so I mean I can control, like, you know, if I want to put 12 legs, I go there and I put 12 legs, and I still have some pins like free. In this here we have 2 different power supply. So basically it's this. So this is the communication protocol. Like I said, it's very simple to use. In this case, we use serial 0. At that point, when we started to communicate the 2 boards, they only had serial 0, which was kind of hard for us because we wanted to use 1 or 2 because the pins are more accessible. So I don't know if they change it by this time, but yeah, that was the one we used. And it's hard because sometimes we wanted to debug the code, and we cannot do this because we are already using to move the robot.
The other thing we still need to do here is to hold that butt switch button to boot the FreeBSD, because the lab doesn't allow us to flash the memory, the bigger one, because they want to keep the Linux.
It's our secret. So no, we can edit. It's very easy. Online, I can do this online. Okay, so this one of the features that we have to think here. Tom used it to move to the position for the servo. So there are differences if you move like this and if you move like this. So it increases the current consumption, and then you don't have enough strength to move the robot. So one of the things that we had to work on this. These are the servos. They are very cheap to buy. They are not the best, but then with the project we just wanted to do a prototype. We wanted to see if it worked, so it was very simple to use. You can find anywhere in China, US, wherever you go, you can find this. It's very easy to attach, and since we bought the frame of the robot, we didn't build it because it wasn't our main goal to build the robot like all the parts. We just wanted to put it together so it attaches like perfectly. So that's why we bought them. And the power source, the main thing for us. So when you're thinking embedded systems, the main thing you have to think is how you're gonna power up your system. You know, you need to give the right current and voltage. And how you're gonna do this? You don't want all your boards burning all the time because of the process of the code. So in our case, since we have two different boards and servo motors, we have 3 different types of power. So we have servo motors is 4.8 volts, and BeagleBone Black is 5, and the other board we have, the driver board was 6. So it was kind of nightmare for us. Like imagine you have 3 different batteries for that. So one of the guys in the lab introduced me to this amazing thing is the DC power supply. So you have the whole like DC power supply here, and this device here, as I can say this, you can control the output speed from 5 to 30 volts, and the board doesn't get hot at all. So it's really good for the system. So we have 2 of these and 2 of these. So we separated. We have 1 power supply for servos, and we have 1 power supply for the boards. Because when you move a servo, you can have a peak of current, and you don't want to damage all the boards. So we decided to separate. The consumption between them, of course, the battery of the servos, you consume more because you have more servos, but then they are still working, you know. So I forgot to say this like 5 or 6 slides ago, but it's fine. We divide the presentation in 2 main sections, the hardware platform and the software platform. And now Vinícius will talk to you guys.
Maybe I'm gonna just repeat something. We said at the beginning, but why FreeBSD? I mean, why not just the usual Debian thing, and you know, because people are using FreeBSD. I was using FreeBSD in my laptop since 2006. And I know companies running, Netflix is running, WhatsApp is running it. It's reliable. Sorry. Okay. So, I was saying.
Companies that use FreeBSD.
Okay. And we wanted to use IPv6 because the IoT was there, and we needed to pay our bills too, and show the coordinators of the laboratory that we could build a product too. So it was interesting to use the IPv6 because it was supported in FreeBSD. The host APD was default in the basic system, and after setting up a Wi-Fi network, we just set it up on IPv6 address and DHCP also. It wasn't mandatory to IPv6, but we did it. And the coordinator just saw that, okay, you can go further, we'll keep supporting you. Okay, and here we are, this. And okay, FreeBSD, for most of you, you know that there were hundreds of contributors and developers, not just students, but PhD professors and things like this, and from different areas of engineering and computer science. And it was not stable at that time, but we knew that we could trust to try it in the BeagleBone, things like this.
I not forget to say that another main thing for us is that we truly have the support from the community. Every time we have something that you want to work on, it's new, or we don't know how to use the functions, and we just, hey guys, can you help us here? I'm not saying that we go there all the time, but that when we really need, you guys are there and helping us. Luis is not here, but Luz, I don't know how you, Luz, and he helped us a lot with the hardware thing. So thank you all.
This is here just to show you our painful day, because we are not allowed to flash the, the thing, and just we need to do this all the time. Hold the boot switch, and we can kill the Linux stack inside. Maybe tonight. Okay, and how it started. I used this board, it's a NVMe 8000. A long time ago with Gen 2, and I remembered it at the day I just did the joke with Edicarla about using FreeBSD in the robot. And when I tried to get it back to the BeagleBSD, it just turned into the crochet. So I started to build the packages with crochet, and it was working. And we installed the Python to code our interface to do the client server thing and control the robot. And then now we tried the release.sh, it's also working to build the image. And for packages, it was automatically there. Just needed to be fun. And when I got comfort with the Poudriere, I just added also MIPS jails for MIPS 32, MIPS 64, and tried to build packages. And I also was getting back to the community and developers and say, hey, this works, you can patch here, you can patch there. And the flow, well. Okay, after we compiled the packages and things like this, we installed the Python, we installed the package we needed. Here is the first interface for the first version of the robot. It's quite simple, just sockets. Listen here and execute the command. Here is the second version, because that we coded based on the Rui Paulo's script for the rover. He used it here also in BSDCan, I think. We are planning to use this to get the visual feedback. I don't know when, but we're going to try to build to use a camera there. Because there is also a support for the Leopard code, FreeBSD, I think, and we're going to try it. And if we need to code a driver or learn to code a driver, we're going to try to do this and use this, not in terminal. These are the positions.
I think I can. Yeah. Can you hear me?
Yes.
Yes. Loud and clear. Yeah. We decided to put this in one of the last slides because we wanted to show you everything that we got to make the robot to. No, it's all good. All good. But I need this. I like this. You can go there now. Thank you. Just like my guy, my turn. Yeah. Oh my God. Yeah. So robot to work, we needed to do it offline. Why? Because we don't have sensors to get feedback from the terrain and the ground. So I created the matrix of front, and it's in Portuguese, but it's front, back, left, and right. One of the very hard thing is when you decide how you want your robot move. You know, you can make it run, you can make it go very slow, but then everything you're gonna do, it will kind of not damage your battery, but then you have to be really concerned how you're gonna use the power you have available. So I try to make it it won't go too fast, but then not too slow. So you have a collection of movements here. Every little one, it's saying which position the leg should be. So it can make it work. So yeah, basically this is, okay, now you go.
I think it's almost the presentation. Okay. The FDT, we use this to turn off some functionalities, some pins from the board. At the beginning, when the I2C bus,
Yes.
the I2C bus wasn't enabled. I think the second one, and we talked to Gonzo, if I'm not wrong, the RC, and he helped us to test it. Also, Luis gave us a really strong recommendation to try it. And the DTS was updated with the base system, and we could use the second channel.
Yeah, because we decided to put a sensor in the robot, you know, just to try all the functionalities and to put more stuff on it. But then when we started using the I2C, we kind of found a flaw in the, I don't know, in the system, I don't know how to say this, we found a flaw. It wasn't, we couldn't use the I2C, it wasn't available. The pins were not enabled to use it, so we contacted the team, and Gonzo was the one who fixed it, and we were able to use. Because I2C1, it's used only by the board itself. You cannot use, so we needed another channel enabled. The same thing we had with serial, that we could only use the 0, not the 1. I'm too ashamed to say this, but we are facing some issues with the batteries because we kept running a bunch of tests. But to prove that the robot really works, I will show you guys a video. Yes. Oh my gosh, I know, he's super excited.
Actually, it works quite well, but we forgot to recharge the battery.
So charging is the answer.
Oh, he put this being dangerous. It wasn't me, so yeah. You explain how much this is.
It's looking right at me. I've been expecting all this time to
Yeah.
jump at you.
We have to leave the few seconds. Is it right? Yeah. Wait.
No, can you put the screen larger?
Make the window smaller and bigger again, make the image full screen. No, not full screen, just smaller and bigger. By resizing it.
Go in video there. Try the full screen. Come on. Okay. one by one to the
It's
computer.
dangerous. You build a robot that's cool enough, you don't have to know how to play the video.
Oh my god, I'm a little bit disappointed because it worked.
Well, keep trying.
Anyways, so I needed to prove to my professor that the robot was working, so we spent almost 2 weeks making the robot move forward and back. And I hope you can see the video, but when things were facing, the robot got stuck a little bit in some parts while it was moving. So the main thing we think it was, it's the batteries, you know, because the software works. And one thing that I thought was amazing with FreeBSD, it doesn't crash. Like I tried, I swear I tried with my zero knowledge in operational systems, but it doesn't crash, which is really good. So we can trust the system. We can trust that the robot's gonna. Yeah, this is the robot Bukin, and then we tried different directions. Goes left and right.
Actually, it's dancing Macarena. Pretty well.
Yeah, we forgot to put this song, but so okay. So as you can see, just goes left and right. We are facing some kind of, I wouldn't say issues, but it's just a small thing. We have, it's not all the terrains that the robot can move. We don't have the correct like kind of boots for the robot. So we chose a terrain that we wouldn't have too many friction with the legs. So we wouldn't force the legs to work. And for this kind of walk, we use a tripod walk. So we have 2 legs one side and 1 leg on the other side, and then you move forward, and then you go like group by group, and that's how the robot works. And to go sideways, we move all the legs, this one back, left one's back, and then front one's right, and then that's how we can move the robot. So I think it's basically this. Yeah. Yes. Yeah, it can dance. It can dance. Definitely can dance. So I think it's basically this. First of all, I want to thank you for the whole organization of BSDCan who give us the opportunity to present the robot. It was amazing for us to do this. It's amazing to know the operational system now, and I hope you guys like the presentation. If you guys have any questions, he's the best guy to answer.
Not true. How did you ever get this thing through airport security?
See, I told you, he's the guy who knows it.
I brought this with a beer in this. Thank God it's not in the US.
So he was going through X-ray, and then people would look at him. Sir, I think you have a spider in your head. And then to explain what it was, you know, and then so he basically brought anything, but he brought some food from Brazil, 2 alcoholic drinks, and this robot, and people couldn't understand. Where are you going? This doesn't make any sense. So we're afraid that we have to leave the robot in Canada. You know, we're gonna donate to university because I don't know how to bring it back to Brazil.
So just some advice for border crossings. You say you're going to a UNIC conference? UNIC conference? The other thing, what I'm really curious about is, have you guys, I know the context you're doing at the university, formulates a little bit, but is there like an instructional way you think you can do this to like replace what all these kids are doing with JavaScript today? Like going this route instead of the JavaScript Lego technique?
That's why we use Python. It's pretty simple, and we put this on GitHub or something like this.
So because the main idea for us is
how students can use this, how, for example, I'm a mechatronics background. I have no idea of operational system, but and then I wanted to bring to my university saying, hey, this is possible. You don't have to buy Arduino and make your thesis about Arduino. You can use something different. You can learn about a computer instead of using something, okay, let's turn on and turn off some LIDs. Great, but how much are you gonna learn with this, you know? So that was, I forgot to say, but in the beginning, since I started the idea, I wanted something to go to academical field, you know? I wanted to bring things to university. And in Brazil last year, I presented the robot as like a lab for mechatronics. So all the steps that you see in class, all the subjects and knowledge that you get in class, you can reproduce and see the robot moving. So that was the idea.
It's more fun than those Lego robots.
Yeah.
So just wondering, so from the presentation I gathered that most of the real-time requirements would be like you send some bytes over the serial bus,
Yes.
and then the other controller is taking care of that, so you don't actually have to worry about real-time stuff with it?
No, we are not concerned with this because we knew the speed, how it would work, and since it's a mechanical project, you don't have to really worry about this because you have the initial of the motor, so it will take time. So, I mean, in the future, maybe if you're thinking about controlling where the robot's gonna go, this is gonna be an issue that we might be facing.
Sure, and then in terms of the engineering of it, how much of this could be offloaded to a supercomputer? You know what I mean? Like, so talking about the latency and like the decisions and that sort of thing. Like, do you have ideas about like how much latency tolerance you'd have for like movements or anything?
Too early for Scott.
Because you can address a lot of them with IPv6. So.
Can I small
Yeah. I don't have any question, just a few remarks and advice. The first one, I'm not sure you will be allowed to do this since you can't reflash the eMMC, but you can modify the BeagleBone Black to add a LiPo connector and use it directly to power the board. So if the lab allows you to solder on the board, I can show you I have a board modified, but take a picture and prove them that it worked, and it could be good because you can use directly on a LiPo battery. So
we got a BeagleBone from the Nickbook George gave us as a donation, and we will just
maybe you can do the modification of this one
in our BeagleBone.
Now we can try all the things, you know, like so the lab won't know what he did.
Also with the BeagleBone Green that I gave you, there's all those sensors available we were talking about.
Oh yeah.
So there's some cool possibilities, environmental sensors and so on and so forth, so there's some cool things you can be doing.
Yeah, we have the world with the robot. We do whatever like it's possible for us, you know. We get many ideas and we try to reproduce them as much as we can. Please?
So from an operational perspective, what's the current battery life?
What's
40 to 50 minutes, you know, but today I found out that I bought the wrong batteries. Yes, today, after 6 months of the project, so we think in the future, we will buy different batteries and then we can have like a larger period that we can use the robot without being charged all the time since it has to be plugged.
And have you assessed for the next generation, you do 3, etc. Have you looked at going from a 32-bit platform to a 64-bit platform?
Well, we didn't think about this because first we wanted to feel comfortable with BeagleBone Black and we can improve more features, and then I think it's how you build solid base and then you can move forward. That's what I think, but we will take this in consideration for next generations.
What's the advantages of going 64-bit for a robot like this?
I'm sorry?
What would be the advantages of going 64-bit?
More than 4 GB. You can have a
memory.
larger memory.
More power.
So you'll be able to do things. And also price can go down. That's going to be lower.
It can go faster.
It just seems like the instructions are so simple.
Oh yeah.
So there might even be an argument that 64-bit might save you a little bit of battery because the atomics run in one cycle, So that means you can have the processor into C1. And that way, just put everybody to sleep if you're not spin locking on 32 bits.
I think this is probably mostly constrained by the motors, not by the controller. Really.
Yeah. So what's your quiescent current when you're not pushing motors around?
It's less than 1 ampere. It's
1 amp?
no, I'm saying way less than
Oh,
that.
okay.
Yeah, because I didn't measure, because I wasn't concerned. So I know I have an idea how much I was consuming before because I was using desk DC power supply. So I almost broke the power supply. So to say, okay, let's move to batteries before we break the whole lamp. So that's it was up to 2.33 amperes per amperes. Yeah. So okay, please.
Oh, yeah. Thank you for the nice talk. So when are you guys going to put FreeBSD on the moon? Mars?
We'll do a moonwalk soon. Not just the man.
What does Aduka mean?
Aduka is a avatar from a game called, I think it's Gunbound.
So yeah, one of the guys gave the idea
Yeah,
to
well,
look at the
just
robot,
gave
and
the
then we
name.
just said, yeah, no, it's not just a robot. We have a name for the robot, and we feel comfortable. It's different,
I think Google Images can show it. We get from there. It was just suggestion.
Anyone else? Please no. Oh, excellent! That's what I was expecting. Last question, just so you guys know.
When's there going to be another BSDCan Brazil?
We are working for next year, and it should be in Rio de Janeiro, but we are not quite sure. For Rio, it's more a tourist place, but I prefer Fortaleza, because we live there.
As one of the few non-Brazilians there, I mean, the food's horrible, the weather, the people, it's not worth going to.
It's real. Yeah, so thank you again.
provide the name of the Okay, so on the contract you don't use because I have a model, I have a Python model.
Now, how do you apply that against
It's a true problem. Using battery from the BeagleBone Black.
I'm already thinking about doing
Thanks very much, actually, you can push it over to my channel.
You can have some kind of
so it gives you every single, which is really great because I can have FreeBSD and then it'll still push out whatever my output is, my one range, so it's great.
I'll send you I send it on the blog post, and I send you the US. It will be much easier and much better because you don't have this is battery
and then VGA outputs as well.
Black and also running from 7 hours on this one.
Yeah, exactly. Yeah,
that's a part of your work.
Yeah, so the service right here.
I'll send you an email with
everything costs me.
Oh!
Yeah.
To take advantage of the inertia and stuff like that. Because I mean, if you're not hitting it at the right time, you might be spending power and doing something there.
You need free.
Yeah.
You need free for a particular attention. Free screen.
For our next project.
It's supposed to be like 4 sockets.
Yeah.
And so it's supposed to be the main design for the system of modules that
So yeah, it's
the
operating system so they're pretty good.
Okay, yeah,
it's fine. Pretty good.
It's not my problem. NGTech, CI NGTech?
I don't know yet.
First embedded project. I was waiting at Mark first to read the specs and the documentation. But the memory maps, in Arabic was good. There was a binder of text that somebody felt important to read in Japanese.
It's a microfiber, it's a ARM board.
But that's one of the worst C books I've ever had. Oh, neat.
I'm not sure that's the switch.
It's time
I'm not sure it's
but this thing there's a collection of solve domains, so there's a we had a certain time to storage, and then you had to decide. Anyway, there's some logic that said was supposed to be if both the sensors
it's smart, right?
Sorry, any business logic and
yeah, the UVM,
but only have a single 9%.
Yeah.
So if I yeah, that's the thing, it's running mechanically. Never, a lot of the time, never zeroes out. Sometimes it does. And you would do the exact opposite, turn like that's what you observe. Just like you'd be driving and think, oh, an open area. Now what would do on the side? Absolutely I found it, I found the code
It's a good one arm.
Early less.
And that's what I need. I'll be short.
Yeah, I've got a
The actual metal bits, that's strange. Is that good or is that something you guys
I don't know the price yet. We need to.
Yeah, no, the metal is
actually. See, I always buy.
I mean, no, this is nicer. We need to speak We'll see when we go back to school, switch to pure graphics.
You guys have
You got one thing? No, it's just
yeah,
and
so talking to this is the say BSDCan
no, this is display. I know, it's probably the same circuit. So
I know, it actually was.
Ah, by the way, you have this. I do with my first one, but yeah, so don't.
Yes, I was putting it's turbo.
Where the legs are.
Okay, so
I mean, the only display I have is this is like so low. I think you could probably change it to like I can take in pretty much anything. Yes. So what do you send me? What's your resolution?
Now it's 1,200.
Yeah.
1280, but
so that's still
yes.
So you want to do 1280 by 720?
I can do like this one.
Which is really no, this is what's you're so soft spoken up there.
I did my university, this piece. The chassis, so
the first we wrote a paper and about the first version of the robot. There's a picture of the whole skeleton.
for us was it way easier since we wanted to go more to the software.
Because the mechanical part is pretty tough to do in your home. We don't have machining tools or anything like that.
Yeah, so we decided, and then we had to draw everything.
Makes sense.
All his we can try it.
And we wanted just to show that it was possible, to control using FreeBSD and BeagleBone Black. So that was the main idea. So we didn't care about the chassis itself.
So do you think you'll get it going by tomorrow, or is it no chance?
I'm sorry?
Do you think you will get it going by, I don't know, tomorrow?
You can try to charge the batteries?
Yeah, we can. I can't promise, but it would be great if you could.
Yeah, if you can get it moving.
Yeah.
Because I think one of the fundamental equations in the engineering side is
There are different things, but the true extent you don't know what IPv4 is, you're not knowing. You have to understand how V6 to V6 mapping or to V6 mapping works. If you don't have to understand how 6 different types of linked local addresses work, because again, you don't have to use them, or you don't have to implement that part of the kernel. I turn on IPv6 for customers without telling them. I do it because I'm a bit of an evangelist. By and large, they don't notice. They do use it. And actually, I get a lot of IPv6 transit for free, so the more people I push to use IPv6, the more free transit I get. I know podcasts, I know big US live. Different address for some other service. Meaning that even if someone knew where your web server was, they had no idea where your SSH server would be. No, it's the thing is that what you do with the firewall sort of changes under IPv6. I mean, it's still useful, but just the yawning great amount of space that you've got sitting there makes the whole idea of port scanning is silly.
Yeah, actually, because I keep all my services on the jails.
Yeah.
So I think it's
Each jail can have their own IPv6. And you've got 64 bits of
I was keeping it like that's what
well, the easiest way to tell, users is to run the rule stack, which means that you look up an address, and if you get a quadruple-A, then you try that. Actually, if you want to set up a method, so you can, for instance, if you're on say web browser,
for the last 2 weeks. I found out getting like 3 and 4 hours
Google
a
for
night.
my ISP,
Like by end of
set IPv6 addresses.
And I was there for a week. I was there from like Thursday, Thursday. So the whole week.
And
because every night I'd be like,
but if you
friend
get that
out,
IPv6
hanging
address,
out.
or you could say Mozilla or whatever,
You know,
it will try
do
the
it again.
IPv6 and if that is
I forgot this
broken,
morning it ran.
it will just try the IPv4 address. And all you'll notice is like an extra second or two long. And you're like, hey, guys, trying to figure out what's wrong with IPv6 when I twigs in the back of your head. Obviously, that's not working. But, like, yeah, I turn on IPv6, and it's starting to divert 20-30% of traffic now. I mean, Netflix, I think, has IPv6. It was just say, hi, I'd like to have Vinícius transfer to say here in this region. And so if I have users use IPv6, generally it's free. Well, first of all, stuff like Google, that's all here. Whether it's before IPv6, that's all free. All that traffic is free. Netflix comes in off of somewhere, I have no idea, I don't know. It comes in off somewhere, so all the Netflix traffic is free. I don't have to pay for it. But the more traffic I divert to the free, the more capacity I have to have more people. And so since IPv6 is free, it's free inside. So the way my ISP works is I have sets of computers for the building what we're trying to do is pretty much everything that is internet or telephone runs through the old CP building. And they'll have wrong. In fact, you'll see it whenever there's something wrong, it's ringed by about 13 trucks generators. Comparison, I don't know if where you live in New York City, 50 or 60,000 street area. That's what it is, 50 or 60 is a similar type of building. But basically, I can throw a piece of fiber in it that doesn't connect. And so that's what I do. I get a wholesale DSL connections coming from Canada. No. That's where I have to meet Bell Canada somewhere. They're happy to meet at 151. So I just have all the one building. That's it. You're sitting there. And basically what we do is DSL connection.
So the pros are, it's insanely flexible. Like, I mean, even with the keyboard, the root systems too. MacBook Pro, I think the lightest is like
wholesale internet. That's why you lack companies like me. Right? Whereas here, Bell is forced by the government to offer
there's a lot of
wholesale DSL.
There's also just
they're required. And in fact, they want to do 5 home, and then we're trying to say, no.
I don't know. Like, what I don't understand is
plug your wholesale. So,
how did Microsoft sell this and not realize what I mean by dumb stuff is like, you can't say land that and use this because basically, say that you have a keyboard back here. There's a magnet so that once the one way to identify that the keyboard is behind the computer is to put like a magnet or something and sense if the keyboard is behind it. With the keyboard, the actual magnet angle of the computer in addition to a magnet. So if you're laying and you have like this like on a mattress and once the computer tilts to a certain degree, the keyboard will just stop like yeah, it'll just like it'll cut in and out because it thinks that you are like tilted. And I'm like, I mean, especially for something that we're pimping and so just put it on your flag. Like I'm running this at actual native resolution, which is why it's tiny.
Well, if you want, as soon as Bell says you can get the media cell, then you can sign up for me, just keep hitting their site. And as soon as
maybe if you're like a startup or something, you just want to use this to draw, then I can understand it. But from like a UI perspective, I find
little smarter
to just mediocre.
Although you can send it in Bridge so you can have FreeBSD on your side as well.
If other complaints, business to service party, the trackpad kind of slows. They listed on the floor the 1 and 2 of a fabric trackpad
And in fact, there's only 2 modems that work
like
with all
your fingers just can't move fast enough over fabric, so it's stupid. This is plastic and it's kind of shitty. Whereas the core uses a piece of glass, so it's actually very, very nice. And it does like gestures and other stuff.
Does anybody have a Mac to VGA adapter we could borrow for talk?
No, I've been debating doing that because my understanding is that the universal Windows apps are not because it's super garbage. My complaint with them on 8 is you can't have something that isn't full screen.
Yeah.
Whereas my understanding on 10 is you can. So now it's like an actual seamless experience when an app switches. But before I needed to use something that like a metro app. Now I can't multitask because
yeah, and the transition is God.
So I'm debating upgrading. Usually I never touch this except for like my own trips. So yeah, like I haven't previously. But now
To get from Vaughn to Toronto,
I haven't ever tried. I know Linux had issues when I got it. I was researching on this. I don't know if they ever got it together.
I was like, where the hell are you doing like storing
Like, given the Surface Pro or like the Surface Book, the price is not an issue. The book is super expensive.
Yeah, Rogers
Like in terms of what it offers, it's kind of risky. But I like it for the weight because I carry it everywhere.
Yeah, that was my explanation that I
just can't.
That it was just because I was trying to think, you know, this was a conference call.
Fair enough. I typically write a markdown and then I'll write it down.
Actually researching some of the boxes we want to know. Yeah, I've seen them at Best Buy, but actually talking to some
I got this for work because, like, not
the worst part about it too was it was 200.
we were doing
plus or minus
touchscreen UI development, and we needed a machine that was like a debugger on. And we realized that this is the only product on the market that actually has a tax and this was like 2 years ago. But yeah, it's.
And there was a 4%
It's just shocking that like when there's 8 people, this was like the device that they're.
Okay, let's get started. Hi everyone, I'm Matt Ahrens. I helped to create the ZFS file system starting back in 2001 at Sun Microsystems, and I work at Delphix. So I'm going to be talking to you guys today about ZFS allocation performance and some enhancements that I've made to it. Okay, so first of all, why are we even talking about this? So whenever ZFS writes anywhere on disk, it has to allocate somewhere on disk to write that to. And it has to be somewhere that is not currently in use. So we have to find some free space to write everything to because ZFS is a copy and write file system. So I'm going to be talking about how ZFS does that and how should it do that. And we'll talk about 2 problems that, that we've addressed with that. So, like, why is that so hard? I mean, you just find some free space and you throw it there and like everything's good, right? So, as I mentioned, ZFS is copy on write, which means that every time you do a write, even if it's rewriting an existing file, we need to find a new place on disk to write it. So we're doing a lot of allocations. And ZFS has variable block size. That means that depending on the size of your file and your settings, you could be allocating a block that's 512 bytes or all the way up to 16 megabytes. And we also support compression, which means that the block could be any multiple of 512. So it could be 7 kilobytes, or 32.5 kilobytes, or 1.275 megabytes. And all of these different allocation sizes mean that fragmentation can become much more of a problem. There's actually 32,000 possible different sizes of blocks that we might need to allocate. Even in the best case where you're still using the default max of 128K and you're using 4K sector size, there's still 32 different sizes, which means that like if you allocate a bunch of one size 4K chunks and then free some of them, then you want to allocate a 128K chunk, we need to find 32 contiguous free slots in order to satisfy that. Okay, so first of all, how does ZFS do this at all? So in the beginning was the write system call. So user-land applications issue write system calls to make changes to the file system. Same kind of thing can come in over NFS write operation, or iSCSI write operation. In what we call open context in ZFS, all that we're doing is copying the data that we need to write into memory and saying, great, everything is good. And asterisk, we're talking about asynchronous writes here, synchronous writes. There's some more stuff going on that I'm going to kind of ignore for the purposes of this talk, but it works kind of the same way. So we record all this dirty data in memory, and then periodically, about once every 1 to 10 seconds, we're going to flush out all the dirty data in the system onto disk. So we might have accumulated like a gigabyte of dirty data, and we're going to go write all that out. And this process is called flushing the transaction group. TXG is an abbreviation for transaction group, and the function that does this is spot sync. So you might hear me use these terms, and they're all kind of interchangeable. We're talking about this periodic activity where we're flushing all of the dirty data to disk. Okay, so so we aren't allocating anything from open context. It's all in the sync when we're syncing things out. So we've accumulated a gigabyte of dirty data, and for each, and that might be like 10,000 blocks. So we have 10,000 blocks that we need to write out. Each one of those, we're going to create an internal data structure called a ZIO that is used to track this allocation and the IO associated with it through all of the stages. So there's kind of 3 main steps to allocation. First, we figure out which device we want to allocate to, and we're doing this for every each of those 10,000 IOs in this example. So the first one comes along and we say, great, we need to allocate this first block. First, we figure out which device should we write to. Then, once we figured out that, we tell the device, hey device, please allocate this. And the device needs to figure out first which metaslab should we allocate from. And then once we figured out the metaslab, then we ask the metaslab to allocate this, and it figures out the actual exact offset. So, and I'll talk some more details about that. But the first stage of that is selecting the device, or VDEV. So what is the point of having VDEVs? Like, why do we even make the distinction between different devices in ZFS? The reason that we do that is because we have this underlying assumption that VDEVs have more, we make the assumption that VDEVs have independent performance. So in other words, if I do a write to this device, then I can do a write to another device, and it won't affect the performance of the first write to the other device. So it's better to keep all my devices busy, because that'll give me the best performance than if I wrote them all to one device. And this is like more or less true. If you have physical disks backing each VDEV, then obviously if I write to this device, then my other hard drive is not involved with that operation. There are other components that are involved, right? They might all be attached to the same HBA, so you're using up some bandwidth resources there. But by and large, they do have independent performance, at least to a first order approximation. So because of that, we want to spread our allocations across all the devices so that our writes are going to all the different devices, so that we are using all the devices to perform this high-level operation of writing out this gigabyte of dirty data. So to accomplish that, we round robin among all the devices. So we just say, allocate the same amount from each of them. And this is like set to 512K. So we say, great, we got a gigabyte to allocate. First 512K from this device, next 512K from this device, next 512K here, then go back to the first one. So the end result is that if we have 3 devices and a gigabyte to allocate, we're going to allocate a third of a gigabyte here, a third here, and a third here. And there's a little bit of an exception here for devices that have more or less free space. We'll allocate a little bit more or less there, but it's not that much more or less. Okay, so once we figure out which device to write to, we need to figure out which metaslab within that device. So what is a metaslab? Each device is divided into about 200 regions. Each region is the same size, and we call those regions metaslabs. And it's at this level in the metaslab that we track what is actually free and allocated. So here we have the underlying assumption that sequential writes are better than random writes. And this is also by and large true, even on devices like SSDs. They do, where they're doing remapping under the hood, they do actually perform much better if you can give them larger chunks of sequential writes so that they don't have to remap as much stuff, they don't have to do as many, they don't have to free as much from their, from the underlying NAND storage. So because of that, we want to try to stick to the same one or small number of metaslabs within each device, because that will keep all of our allocations more or less localized within that device. Rather than if we were to spread it out over all the metaslabs, that would mean that the writes would be very scattered across the device. So sticking with a small number of metaslabs keeps the writes localized. So the first thing we do is we're going to find the best metaslab. So the best metaslab we define as the one with the most fragmentation-weighted free space. What does that mean? So it's the most free space, so whichever metaslab has the most free space, because we assume that's going to be like the best one, the easiest one to find space to allocate from. Fragmentation-weighted means that if we have 2 metaslabs, 2 regions, they both have the same amount of free space, but one of them, their free space is in bigger chunks, then we're going to give more weight and prefer to allocate from that metaslab. So for example, one metaslab, all of its free spaces in 1 meg chunks, we're going to say that's a great one. But if one has the same, another one has the same amount of space, but they're all in 1 kilobyte chunks, it's going to be a lot slower to write there because we're going to have to spread it out over all these little 1K fragments. And then we're going to stick with that metaslab. So we want to stick with the metaslab because otherwise we would just have all the metaslabs with the same, fragmentation-weighted free space and to allocate a little bit from each of them, decreasing each of them a tiny bit. We'd end up spreading our writes all across the whole device. So we stick with the metaslab that we've chosen until it's more than 70% fragmented. And that means that the average free chunk size is around 32 kilobytes. So let me give you an example here of what this percent fragmented really means and how we calculate the fragmentation-weighted free space. So each metaslab is a region of the disk. Each metaslab uses this data structure called a space map to keep track of where exactly the free space is within that region. And each of these space maps has a histogram of how big each free chunk is, or how many free chunks there are of each size bucket. And this histogram is always loaded in memory. So we have this available when we're trying to decide which metaslab to select. So the stars here show kind of the histogram visually. And what we've actually recorded on disk is the num chunks column there. So we know, for example, we have 50 chunks whose size is about 256 kilobytes. We have 157 chunks whose size is about 128 kilobytes, and so on. We multiply these first 2 columns to get this free space. So we know that we have 12 megabytes of free space in chunks of size 256, 200 megabytes of free space that are in chunks of size 128. Then we have this fragmentation, like statically defined hand-wavy table that just says, technical difficulties. Okay. You can still hear me. So basically this table is just hard-coded, and it defines like, okay, we're just gonna say that if the chunks are 1 kilobyte, that's like totally 100% fragmented. If the chunks are size 128 kilobytes, that's halfway, 50% fragmented. And you know, this table describes the rest of it. And it gets to 0% fragmented is 1 megabyte and larger. So we multiply the free space by the inverse of this percent to give us the fragmentation weighted free space. So, you know, in the 128, in the 1K chunk, we say, oh, we have 2 megs of space there, but it's 100% fragmented, so it counts nothing towards our fragmented free space, only 0 megs. But, you know, here at 128K, we have 200 megs of free space, it counts half, so we count 100 megabytes. So we add up all of these, and it gives us 459 megabytes of fragmentation weighted free space. And then we use that to calculate the overall, the fragmentation percent for this metaslab, and then the same kind of thing works on the aggregating up to the whole pool level, where we're figuring out, you know, what chunk sizes the free space is in, and then using this table. The table is basically based on experience of like, if you have 1 meg free chunks, then performance is like nearly as good as if you had infinity size free chunks. So we'll call that not fragmented at all. And you know, 128K is like, oh, you're still like pretty good, so it's 50% fragmented. Obviously, we could have chosen to define this table differently, and it would have meant something different. But this gave us a good kind of spread over reasonable sizes of free chunks that we see often. Questions about this? Yes.
Did you generate that with that table just from heuristic knowledge, or is that a command that you use?
The fragmentation percentage?
Yeah.
No, that's just like heuristical knowledge, yeah.
So in other words, we shouldn't actually put too much, try and interpret the fragmentation percentages we see too literally. It just sort of like tells you where it is on that scale.
Exactly, exactly. So, I mean, the only real literal interpretation is to just go backwards and say like, okay, well, if you're at 70%, then, you know, the average free chunk size is 32K. But that, you know, that's only as useful as far as the, like, if your distribution is like a normal distribution. If it's like lumpy, then, you know, who knows?
That's fine, yeah.
You can use ZDB to get a histogram from each space map to kind of get an idea of what's happening.
Yeah, so you can use, I'll just repeat it for the recording. You can use ZDB to get a table that looks like this with the stars and the histogram of each metaslab or each VDEV. That gives you more accurate information, but we wanted to boil it down to just one number that could be compared. We intended it not to be used so much to say like, oh, that means my average chunk size is 64K, because like, well, then what? What does that tell me about anything? But more to be used as a relative comparison between different pools, and so that people could accumulate some kind of institutional knowledge about like, well, on our workloads, we know that like once you hit 70%, that actually means something. It means that the performance is dropping off, versus somebody else could say, well, our workloads are, you know, much easier, so we can go into 90% without performance dropping off. But it's a measure of the performance that you should expect of your writes. Okay. So great. So now we understand what it means to be 70% fragmented. So why? So now, of course, everybody knows why we said to stick with it until 70% fragmented, right? Like, that totally follows from what I just said. Okay, moving on. Yeah. So that 70% fragmented is like also completely arbitrary. And there's nothing magical about it, and there's kind of some big questions here, like what if all of our metaslabs are more than 70% fragmented? Does that mean that we're just going to be like switching between metaslabs on every allocation or something? Like that doesn't sound good. So because of these problems, we have implemented a new way of doing metaslab selection. And that is, rather than starting with the metaslab with the lowest fragmentation, with the most fragmentation weighted free space, instead we're going to start with the metaslab with the most largest free chunks. So in other words, we're going to find the metaslab that has the largest class of free chunks, and then the one that has the most of that size. And we're not going to work on it until some arbitrary number. We're going to keep using that metaslab until there's another metaslab in the pool that has a free chunk that's 4 times larger. And this is work from my colleague George Wilson that is going to be posted for review very soon. So let me give you an example. Let's walk through an example here, which hopefully will help explain this. So here I've shown 4 different metaslabs, and I've shown them ordered in the way that they would be ordered by that metric, so 1, 2, 3, 4. So if we look at what is the largest free chunks? So these two, their largest free chunks is 128K, so that means they come before these ones whose largest free chunks are in the 512K bucket. And then within that, we're going to look at how many chunks they have of that size. So this one has 2 chunks of size 128, and this one has 1 chunk, so this one comes first. So we'll first select this metaslab, and then we'll keep allocating from that metaslab. We'll allocate all the 128K chunks, then we'll eat through all the 512K chunks, and then we'll have left, the largest ones will be 256K. And then we'll see, oh, well there's another metaslab in this pool that has chunks that are 4 times larger. So we have 256, and this guy has 128. So at that point, we'll reevaluate, put this one back into the pool, and switch to the new best metaslab. So this method works regardless of kind of how good your devices are, right? So like if all your devices are at 10% fragmentation, it's still going to select the best one, stick with it for a long time, and like maybe in that case your biggest chunk is 1 meg. You're going to stick with that, or I guess this is 1 meg. If your biggest chunk is like 128 meg, it might stay there. It's going to stay there for until you get down to the ones with a 1/4 meg. Or if you have a really, really fragmented pool, maybe they're all 80% fragmented, it's still going to stick with the best one for a little while until there's something better to go off of, rather than arbitrarily saying like, oh, like once you hit 70%, then it's time to do something else. Okay, I'm going to be moving on to a different topic. Any questions? Yes?
So you've selected a chunk which is 1 megabyte. You're going to be writing into this. Presumably you don't fill it all at once. So once you've written to the first 3/4 of that, do you then say, oh, the remainder of that chunk is only 256K, you should switch? Or do you say, let's finish the rest of this originally 1 meg chunk?
Yeah, that's a good question. So that gets into the policy of like, once we've selected this metaslab, how do we select the specific offset within it to allocate? So there's actually several different allocation policies that can apply at that level. But most of them, and the default one, uses like a cursor that keeps track of like, where did I last allocate? And it's going to prefer to go there if there's still enough free space there. So essentially we'll like find that 1 meg chunk, start at the beginning of the 1 meg chunk, keep allocating until we can't fit the next allocation in the remainder, and then we'll go to the next biggest chunk. So in this case, we'll find another 1 meg, go through that, and then we'll find the next biggest, which is the 512, and work through that.
So the question of switching to a different slab only happens when you finish the chunk?
Yes. And I guess what I was saying is, and the question of switching to a different chunk only happens when you finish that chunk.
Yeah.
Other questions on this topic? Okay, so next I'm going to be talking about a problem with allocation that can occur if you have if the devices in your pool have different write performance. So, why would that happen? Cool. Okay, so in this pool, we have a whole bunch of mirrors, and some of them are bigger than others, and some of them are more, the smaller ones happen to be more fragmented. So that means that we can expect, the point of the fragmentation metric was to tell us how fast is it going to be to allocate and write to these. So these ones are more fragmented, it's going to be slower to write to them. These ones are less fragmented, it's going to be faster to write to them. And you can end up in a situation not just if you've horribly misconfigured your pool with different sizes of devices, but even in normal circumstances, you have all the same size devices, but you added some of them more recently. Well, when you add those devices, they're totally empty, whereas the other ones are probably mostly full. That's why you added the new device. And so writing to the new device is going to go really, really fast because you have huge swaths of free space. Writing to the full devices is going to be much slower because their free space is probably all fragmented. You can even end up in this situation if you've added all the devices at the same time, and they're all the same size, and they're all from the same manufacturer, they're all the same model, just due to natural variations in what you're allocating and freeing. Some devices might be have slightly better free space that we can allocate from than others. And there might only be a 10–20% variation there, which is not that big of a deal, except for the fact that it means that you're essentially leaving 10 or 20% of performance on the table. So remember, I said that when we are selecting which VDEV to allocate from, we just round robin among them, allocate more or less the same amount to each one. So that's kind of what this is showing. So on the x-axis, this is showing the span of time of one transaction group. And on the y-axis, the number of outstanding IOs. So we start by, we have this 1 gigabyte of space to allocate. We allocate it evenly among all the devices. That turns out to be 1,300 IOs to each of these two devices. One of these devices is fast, so it's able to burn down all of this, do all of its allocations, do all of the writes to those offsets, and complete it by this time. Meanwhile, the slow device is still working on it, and it takes it all this much longer to actually complete. So that means that during, whatever this is, 2/3 of the time, the fast device is just sitting there idle, because we only allocated the same amount to it as the slow device. So you might see this, another way of observing this is if you use z=iostat, you can sometimes catch it writing, but not to all the devices. This is sometimes hard to see because oftentimes the time scale of one transaction group is only a couple of seconds, and this is only outputting once per second. So it's easier to see it in the kind of sub-second granularity graph that I showed before. But you can definitely catch it here sometimes. If you see this, then you have this problem. So how do we fix this problem? Basically, we know that we've already postulated that these devices are slow and these are fast. So we just want to allocate less to the slow devices and more to the fast devices. The question is, how much less and how much more? So we want to arrange it so that we're utilizing all of the available write bandwidth. In other words, we're keeping all of the devices busy writing our data all the time. So the solution here is to allocate incrementally as we go through the SPA sync. So instead of allocating the whole 1 gigabyte up front, partially out to each device evenly, we're only going to allocate a little bit to begin with. We're going to allocate 100 writes to each device. And then, as each write completes, we're going to allocate another I/O to that device that completed the I/O, so that we keep all of the devices with 100 allocations outstanding all the time. So the end result is that as you do more work, we give you more work to do. So we keep all the devices busy all the time, and we're going to end up allocating more space from faster devices. And as those fast devices, because we're allocating more, they're going to fill up faster, right? But then there'll be a natural balancing where, like, the fast device, as we allocate more stuff from it, is going to get slower because we're going to be filling up more of its space and creating more fragmentation there, and we'll allocate less from it. So on real-world workloads, we've seen a doubling of performance based on just this change. So this actually saved us a lot of money from having to buy new storage.
Is that number of 100 allocations tunable?
Yeah, that's tunable. And I didn't have a good graph to show it, but because it's keeping 100 allocated to all devices at the same time, you can think of it like, so you can think of it as if we stretch this period where they all have the same number out really, really far, right? So you have both lines parallel here, and then one drops off quickly and one drops off slowly. So you still have a little bit of time where one device is idle, where the fast device is idle, and that amount of time is set by the 100, right? So I do all my 100 instantly, but this guy takes 100 milliseconds to finish his last 100, and so for those 100 milliseconds, this device is idle. So you could turn that down to get kind of better, to have less idleness, and you might want to turn it up if your device is able to benefit from having lots of IOs outstanding all at the same time.
That's what I was thinking. Like an NVMe can do 63 concurrent operations at once.
So you might want to increase it in that kind of situation. Yes, there was another. Yeah.
I'm just curious. Does it actually mean that you will be using more space on faster devices?
Yeah.
Over time?
So if you had two devices that are empty and they have different inherent performance characteristics and they're the same size, we're going to write more to the fast device, filling it up faster, and then essentially we'll end up in a steady state where the fast and the slow devices are different fullness amounts, but they both deliver the same rate performance. Right, so that the fast one will get really fragmented, but it'll still be as fast as the slow one, which is not that fragmented.
Does it also mean that you will get a little bit worse read performance later on when you're reading, because you now have less concurrency to hold the data down?
Potentially. If the devices are kind of the same, do the same thing for reads and writes, like spinning disks, then it's going to all work out. If they have very different performance for reads versus writes, then there might be some interesting issues there. Excuse me while I hopefully fix my technical difficulties. Was there another question before we move on to the next topic?
What kind of data structure is the space map?
Excellent segue. I'll next be talking about on-disk data structures for tracking space allocation. So, as I mentioned, each VDEV is divided into metaslabs. The way it works right now, it's divided into about 200 metaslabs. And the point of the metaslab is to track exactly what space is allocated or free within that region of the disk. So the space map is the on-disk data structure that tracks this. It's a log of allocations and frees. So in this example, at the beginning of time, we assume that the metaslab is entirely free. Then we allocated this block, which was 3 sectors, 4, 5, 6, 7, or 4 sectors. Then we allocated another chunk. Then we freed some part of that first allocation. Then we allocated some more stuff. And then there's some unused space. So the next allocation or free will be appended here to the end of the space map. And this space map is an object. It's stored in the MOS. The MOS is an object set that stores all the pool-wide metadata. But it's stored within the pool. There's no like special place for it or anything like that. So we just keep on appending to this as we do allocations and frees to this metaslab. But obviously we can't append forever because we would use up all the space in the pool. So you might end up with a situation like this where we've done an allocation and then we freed that space. And then we might happen many times over where we allocate a given place on disk, and then later we free that place, and then we allocate it again, and then we free it again. So periodically we condense the space map by writing it out just with the current state. So we're like, okay, we allocated, freed, allocated. Great, so at the end, it's allocated. We just need to write one allocation entry for that block. Any questions about this? So that, this is the on-disk data structure, but this is not very convenient if we want to know, like, is this offset allocated right now? So, when we're going to allocate, we need to know, like, where is the biggest free chunk? Or what if I allocated here? Is that okay? Is there free space there, or is it allocated? This data structure, it tells the information is encoded there, but it is not easy to find it, right? You'd have to like scan the whole thing to figure out where if what you're looking for is allocated or not. So to allocate, we have to know exactly which parts of the metaslab are allocatable, in other words, that are free. So to do that, we load the space map, which means that we read the whole thing from disk, and we generate this in-memory data structure called a range tree. So the range tree, conceptually, you can think of it like this number line where it's just telling us like, this range is free, and this range is free, and this range from 5 to 7 is free. So each of these circled things is like one entry. Obviously, this could be like, there could be 1,000 numbers in there, but it's only a constant amount of space because it just says from 5 to 1,000. And then we're actually representing that in memory in like a balanced binary tree. There's actually 2 of them. One is sorted by offset here, so like 0, 3, 5 increasing offsets, and another one that's sorted by increasing size. So like this one is size 4, size 1, size 1. So what we've talked about so far, like a metaslab is one-to-one with the space map, which is one-to-one with this range tree. But conceptually speaking, like the metaslab is the region of space and the kind of code that is in charge of that region of space. The space map is the actual on-disk representation of the allocated and free space, and then the range tree is the in-memory representation. And we'll get into some examples of where these data structures are used for other things later on. Any questions about these data structures? Yes?
So, do you calculate the in-memory during an import from the on-disk representation?
No. So we only need to generate the range tree when we're doing allocations from that metaslab. So normally, so this is another advantage of sticking with one metaslab for a while, is that we load that metaslab, meaning read it, generate this range tree, and then we're going to do a bunch of allocations from it. That might happen for minutes to hours before needing to load another metaslab from disk. So we can do freeze to any metaslab, whether or not it's loaded, because freeze, they're giving us the block and saying, this block I don't need anymore. Great, so we can figure out from the offset in the block which metaslab it is, and then we just append an entry to the end here that says, oh, this part's now free. We just trust that it is actually allocated. Versus when we are doing an allocation, we need to know exactly which regions are allocatable, so we need to load it into the range tree, and then we're going to append alloc entries to the end here. So how exactly that works? When we are syncing out a transaction group, we keep track of, each metaslab keeps track of what allocations, what parts of it have become newly allocated and what parts of it have become newly freed. And we keep track of those in range trees, different range trees. And then at the end of the transaction group, we're going to like iterate over each of these range trees and basically convert them into the space map. So the range, the allocation range tree might say, okay, in this transaction group you allocated from A to B and then C to D. We're going to go right to the space map. Okay, A to B is now allocated, C to D is now allocated. So this is like hopefully relatively straightforward, but one of the really interesting aspects of it is the dynamic behavior. So typically we're doing a lot of frees every transaction group. And this is true, well, this is not true if all that you're doing is like appending to some giant files, ingesting a lot of data. But it's very true if you're overwriting any files or freeing any files, then we're going to be freeing a lot of space. And the frees tend to be scattered across all parts of all of the disks, which means that we need to, which means that we're freeing space from every metastop typically. So usually, in every transaction group, we're appending to most of the metastops. And this can result in a lot of IOs. Typically, we see like roughly 600 IOs for each VDEV for each transaction group. 600 is because there's 200 metaslabs in each one of those space maps. We typically have 2 levels of indirection. So we have the data block of the space map and then 2 indirect blocks above that need to be modified. And then obviously this is assuming that we're only writing like less than the block size. If we're writing multiple blocks, then you'd have 3 data blocks and 2 indirects or something. Okay, so that's unfortunately not the end of the problems. So also reading space maps is stuff. So you're asking about like, when do we read these data structures from disk? The answer hopefully is rarely, but it can be quite expensive because primarily because the space map block size is only 4 kilobytes, which is really, really small. So I've seen like with even with only a 1 terabyte VDEV, the space map can be as large as 5 megabytes, which is over 1,000 blocks, which means that when we read in the space map, we have to read 1,000 blocks from disk, which could take several seconds. So why is the block size 4K? Well, it's 4K because we're appending to every space map, every transaction group, and if it were larger, we would be writing even more data, right? Because we have to, even if we're only appending 1 record to the end of the space map, we have to modify that data block. So if we increased it to 128K, then we'd be writing 25 megabytes every transaction group, which means like we could end up using like 6% of our bandwidth overhead just for appending these space maps. And the goal here is like you don't have to think about this ever at all. Allocation is simple and it just works, and you don't have to go to a talk that explains why all this stuff is horrible. So 6%, not great. Another problem that can occur is that even though we only have a few metaslabs loaded from each VDEV at once, those metaslabs can cover a huge range. So if you have like a 10 terabyte VDEV, which I think very soon will be one single device, but even today, you often have this if you have like, let's say you have 5 2 terabyte devices in a RAID-Z group, then that's a 10 terabyte VDEV. So we've seen cases where the range tree of the loaded metaslab can take up to 300 plus megabytes on a device of this size. And that's based on because we could have like 5 million segments in the metaslab. So then multiply that by your number of devices, you can end up using a huge chunk of your memory for this overhead. So how could we solve this? Maybe we should be using a different number of metaslabs per device. Like right now we're doing 200, but maybe if we had more metaslabs, then each metaslab would be smaller, which means that it would use less memory for for the loaded space maps, and it means that it's smaller, so it would be faster to load it because you know, it would only cover a smaller region. But then, you know, on the other hand, maybe we should have fewer metaslabs that are larger, because then we wouldn't have to append to as many every transaction group, so we wouldn't have to do as much I/O. And you know, maybe the metaslabs, maybe rather than having a fixed number of metaslabs, maybe the metaslab size should be fixed, so that like as devices grow, metaslabs don't grow with them, right? When we came up with this number 200, this was like over 10 years ago, when you know, a big device was like, I think still less than a terabyte. So another thing we could do to improve the performance would be to change the block size that we're using to store the space map. So right now it's 4 kilobytes, which is really tiny. So maybe we should make that bigger. If we made it bigger, then it would be faster to load it because there would be fewer blocks of the space map. But then again, like maybe we should keep it small, because keeping it small means that we use less bandwidth to write it out when we modify it every transaction group. So like having more metaslabs with bigger space map sounds really good, except for this problem, this fundamental problem that we keep coming back to, which is that we have to append to most metaslabs in most transaction groups. So, yes, go ahead.
With the new allocation thing where you're trying to stay on the same metaslab longer, will that mean that if your pool always used that, eventually you wouldn't need to write, you wouldn't be writing to as many metaslabs at once? So when you're freeing old stuff, it was mostly contained in a smaller set of metaslabs?
That would be true only if you had never consumed the whole device, right? Like, the scenario you're talking about is like, essentially, what if some of my metaslabs are totally empty? Then there's nothing to free from them, so I can't be appending to their space maps. So that is true, but in practice, like most people like kind of fill up their storage space, and so that's like a nice corner case optimization, but it doesn't really help us in the common case, unfortunately. Yes.
I don't think the other slabs need to be completely empty. I think generally there's a tendency that data that you have written more recently is more likely to be free soon. So there's going to be a skew towards removing towards
Recently written data.
the slab you just united to.
Yeah. So
you might end up with a lot of slabs that you're not creating data from at any particular moment, even though eventually you would lift it all.
yes, like totally, you might end up getting lucky here. And it's certainly true that like things that you allocated recently are most likely to be freed. But the problem is that even if you free just one block from a metaslab, we have to append to it and incur the cost of those like 3 writes. And so like, yeah, like this, I'm sure there's if you look at the distribution of like frees per metaslab, like most of the frees would be going to a small number of metaslabs, but almost all the metaslabs would have at least 1 free per transaction group. I will certainly concede that that is not true for every workload. It's definitely true for the workload that happens at my company, where we're using databases which have a lot of random writes, and everybody likes to keep their storage pools as full as possible, keeping old snapshots for forever. But I can certainly imagine other use cases where this wouldn't happen. In which case, you're great. Don't worry about any of this stuff. Was there another hand before I move on to how to address this? Okay, so how do we fix this? So I was saying we keep running this fundamental problem that we're appending to most space maps and most TXGs. So the solution is, let's just not do that. Let's not flush the modifications to every metaslab, every TXG. Instead, let's just keep track of those in memory and then flush them periodically. So every metaslab will keep track of a range tree that tells us, like, here are the allocations that have been performed but haven't yet been written to my space map. And then another range tree of here are the frees that have been performed but not yet written to my space map. So how do we do that? These So we want to keep these trees not overlapping with one another. So for example, if we allocate a given block and then we free it and then we allocate it again and then we free it again, we don't want to create multiple entries in here to try and keep track of that. Instead we say like, okay, I allocate it, I put it in the unflushed allocs tree. Then if I free it, rather than putting it in the unflushed frees, I'll remove it from the unflushed allocs. That tells me essentially we're keeping track of the delta from whatever is on disk in the on-disk space map, right? It's saying, I allocated it, great, now I have this allocated that's not on disk. I freed it, oh, okay, great, well, now there's no change from what's on disk, so I don't need to keep track of that anymore. So now when we load a space map, when we load a MetaSlab, the space map doesn't tell us all of the allocation state. So first we have to load the space map, and then we need to apply the changes that are in these in-memory unflushed allocations and frees. So once we've done this, then we can say, all right, great, let's just flush like about one MetaSlab per TXG. So the changes eventually will get into this MetaSlab space map, but we'll just only come around. So for a given MetaSlab, it's only going to get its changes flushed, once every couple hundred transaction groups or something. That way, we're going to have a lot of, when we do flush the changes to the MetaSlab space map, we're going to have a lot of changes to do. So we get good efficiency there. We're appending lots of changes to a small number of MetaSlabs, each transaction group. So what if we crash? Right? I'm saying we're keeping track of all the stuff in memory. Well, if we crash, we're going to lose all these unflushed allocations and frees, and then we're going to get confused about what's really allocated when we open the pool again. Questions before we get this is kind of the big idea, and then we'll get on to how to address these other problems. Are there questions, or do folks understand what I've explained so far? At least a little bit of understanding. So, right, so we can't lose these. So the solution to that is we're going to keep track of these unflushed changes in one giant space map. So every VDEV, we're going to say all the changes to all the MetaSlabs that haven't been flushed, we're just going to dump them all into one big space map. And then, if we crash, well, great, we have this log, and when we start up again, we can read the VDEV's unflushed log to reconstruct what we had in memory before, which was each MetaSlab's unflushed allocations and frees.
It's beginning to sound remarkably like journaling. I mean, you're doing the same thing essentially.
I mean, it's certainly similar. It's a similar concept, but applied in a different way. With the different data structures. Okay. Other questions? Yes.
Does this Uber space map get into the slog if you have one?
No. So none of this needs to be involved with the ZIL or logging at all. So everything that I've been talking about here, this is all happening when we're fleshing out when we're syncing out the changes to one transaction group. So I don't know if any of you were here for Kirk's talk this morning about UFS. He talked a bunch about maintaining consistency by ordering writes in soft updates, that kind of stuff, which would be very this kind of scheme that I described would be very difficult if we were trying to do that. But thankfully, because ZFS is copy on write, all these changes that we're making in one transaction group, we can make arbitrary changes to any files and any data structures that are interrelated, and all of those take effect atomically when we update the actual Uber block. This is kind of fundamental idea of ZFS, that this whole batch of changes that we're writing out in one transaction group, they all succeed or fail at once. So it's very easy to make interrelated changes, where we're saying, okay, we're writing out a new block, that's forming an allocation, and we're recording the fact that it was allocated in this other data structure that's in some totally other part of the tree. but they all take effect atomically. And the same thing applies with this VDEV space map. Other questions? Okay, so a couple of more questions that we might want to look at here. So I said that we should just like flush one metaslab every transaction group so that we eventually the data gets flushed and we don't need an unlimited amount of memory. But is one really the right number? So I thought about like what do we want to control here? So we want to limit the reconstruction time first of all. So we're appending to this per VDEV space map log, and we need to read it when we start up. If that takes a really long time, that's going to be bad because it impacts our pool import time. So we want to limit the size of the VDEV space map, and probably some fixed size, like it shouldn't be more than a gigabyte or something. Then we also want to limit the amount of memory we're using so we want to limit like the number of segments that we have that are using allocating memory in this excuse me, in these unflushed allocant free trees. So the idea is like every transaction group, we will flush at least one metaslab, and then we'll just keep flushing more metaslabs until we've satisfied these conditions of, the VDEV space map is below some threshold, and the amount of memory used by the unflushed allocant free trees is below some threshold. And I guess one thing I should say kind of inherent in here is that as we are flushing the metaslabs, we will find that the VDEV space map, like the older parts of the VDEV space map, become totally unneeded, right? So as we, if we, like let's say we're flushing one metaslab per transaction group and there's 200 metaslabs, we just go round robin, then it means like we only need at most 200 transaction groups in the VDEV space map. And stuff that's older than that, we can throw it away. So once we throw it away, we aren't wasting space, and also, more importantly, we aren't needing to read that when we start the system again. So the end result of this is that this scheme solves the needing to append to every space map every TXG. So because of that, we can increase the number of metaslabs without any penalty. If we increased it to about 1 metaslab per gigabyte of storage, then the loaded metaslabs would use a 50th as much memory, and loading a metaslab would read a 50th as many blocks. This is an example with a 10 terabyte VDEV. And then we can also increase the space map block size to 128K, which means that loading a metaslab only needs to read 1/32 as many blocks. And if we do both of these things, then they multiply together. So loading a metaslab only needs to read one, what is that, like 5,000th, 1,000th as many blocks. And then because we're only appending to 2 space maps per transaction group, one being the one metaslab that we're flushing, and the other being the VDEV specific space map, we only need to do 1/100th as many IOs and using 1/10th as much bandwidth. Great. Questions about this? So this work I have been working on implementing. It still needs a little bit more work before it is integrated, but this is coming. Yes.
How soon? A week, a month, a year?
More like a year. So the other 2 changes that I mentioned, those are both going to be out for review soon. So that's, I would say, like weeks to a month. This is going to be, come back next year. Hopefully, we'll be able to say that this is integrated.
Awesome.
Other questions? So I have one more thing. Oh, did you have a question?
I was just curious. I mean, have you got enough of it done yet that you can see whether you're getting those kind of improvements?
Yeah. So I've actually implemented basically everything except for this last slide of like figuring out how many to flush per transaction group. And yeah, we've seen really good improvements here. This stuff pretty much all pans out as theorized because it's like, it's very basic and theoretical. Like if you have fewer of these things, then there's, if they're smaller, then there's less stuff in each of them. What we have yet to do is measure like under a real world workload, like how much actual bottom line performance do you win, right? Like obviously the overhead here is going to be much less, but how much does that matter on a real world workload? Based on measurements that I've seen before, I think this is going to be on the order of like 10%, maybe 20% in the extreme cases. But that's the kind of order of magnitude improvement we're talking about. Unfortunately, not the like twice as fast kind of stuff that we saw where we were just like letting disks sit idle. So I have one more announcement to make, which is the OpenZFS Developer Summit Conference. So this is a conference that we hold every year. This is going to be the 4th year that we've done it. It's going to be this year, September 26th and 27th. That's a Monday, Tuesday, just like previous years. It's going to be in San Francisco, just like previous years. As with previous years, the first day will be talks. The second day will be hackathon, where you have a chance to like work with folks who maybe you don't see every day. This is primarily for developers, folks who are working with the ZFS codebase. We have pretty limited space, but registration is now open. So please, if you're interested, grab some of that limited space because we anticipate selling out. We have not increased the size of the conference since last year. So we wanted to keep this small, small intimate feel where there can be discussions. Right now, we're primarily looking for folks to submit talks and also for companies that are interested in sponsoring the conference. And we have 2 early sponsors, Delphix and Intel, who I'd like to thank. So I hope to see some of you there. And I hope to hear from some of you with talks. Send me email. We're looking for just very short proposals of what you'd like to talk about. Thank you. And I'll be here if you have other questions that you want to talk about. Yes?
One vital question. How do you feel about people pronouncing it ZFS?
You can pronounce it however you like. I'm cool with all pronunciations of ZFS. That's just how I say it.
Can I pronounce it RISC-V?
You can pronounce it however you like, but people might be confused.
I thought you liked your wife.
That's a deadly mistake.
So historically, it's been pretty quick, like usually less than a month from when it goes into the most, it shows up in preview. And obviously that's the same head. And then
And then when we set it to 10 seconds to see if it's just it got slower. So random data point. Yeah, I was really wrong. One of the like a bunch of benchmarks actually. Yeah, we found the exact opposite. But it was on the sliding glass, that's true. But on SSDs, that wasn't the case. And I don't know if it's to do with between SAS SSDs and SAS. This was the most aggressive 8 watt and 1860 watt. And it was that really surprised me. So I didn't sit with the word. I was hoping it would be like, explain that.
They're all the best birds. Yes, they are.
We got some pretty big wins by working on all of these. And at the end so far, you see that being George, has done this stuff and a bunch of other stuff random and we've gotten like, I think at least twice as fast.
Whatever that was.
Oh shit, there are several.
We create the CIOs in this case, order, like one file, but then basically you can allocate, and so they go basically to the session, right? And then after that, so George added like a new state where when we, it's kind of about just like what do we need for the allocation to allocate later. It also like when it's waiting to allocate, we put it in the sorted data structure. So it's sorted by so when we actually allocate, we're pulling them off again in the right order, in the right order, which gives more I think there's always, I suspect there's more to it, but maybe I'm not starting to kind of benchmark, almost every other person is one. Suddenly, there was a tie. There are many